Now, what is thermodynamics? It is branch of physics that deals with heat, temperature, and the work. So now, in thermodynamics, we consider some system. So what is a system? It is the region of space that is of interest. So we are interested in the thermodynamic properties of this system. Okay. So everything else apart from the system will be called as surrounding. So what is surrounding? Everything that is not included in the system, but that will be whole universe, right? But we don't have to consider whole universe. We just have to consider the part of universe, or only that much part, that many things which will affect the system, which will affect the thermodynamic properties of the system. Okay. So that is known as our surrounding, right? So now there are three types of a system: thermodynamic system, an open system, a closed system, and an isolated system. So what is an open system? So if the energy as well as matter can be exchanged between the system and the surrounding, then it is known as an open system. Okay. Now, if only the energy can be exchanged but not the matter, then it will be called as closed system. Okay. So there is some boundary. Okay. There is a wall between system and surrounding, and no matter can no matter can pass through that wall, but energy can pass. Such a wall is known as a diathermic wall. Okay. So if system and surrounding is separated by a diathermic wall, then it is known as closed system. And then there is next the isolated system. Isolated means isolated. There is no exchange of heat and matter. Okay. From the isolated system to the surrounding, or vice versa. Is this thing clear? So there will be so many theoretical things that we'll see, and they will be simple. Now, what is a thermodynamic equilibrium? So a system is said to be in thermodynamic equilibrium with the surrounding when its macroscopic variables. So what are macroscopic variables? The bulk properties. Okay, properties of bulk matter, right? So variables like temperature, volume, pressure, mass, etc. These are macroscopic variables, and they do not change with time. If these macroscopic variables, temperature, volume, pressure, mass, they do not change with time, then we say that the system is in thermodynamic equilibrium with the surrounding. Okay. So now, why are these variables called as macroscopic variables, and why not microscopic variables? What is the difference between macroscopic and microscopic? Do you know this? Yes, no? So these variables are known as macroscopic. Macro means bulk. Okay. Macro means bulk. So here we don't consider the properties of each and every constituent. What is constituent? It might be an atom, it might be a molecule. Okay. So a system, for an example, a gas, it might be made up of what? Atoms. Okay, thousands, actually millions of atoms and millions of molecules. So we don't consider the microscopic properties, the properties of all those atoms. Okay, so we don't go into the microscopic details. If we want to measure the temperature, we don't need to know about the temperature of each and every atom, right? And that's why this is known as the macroscopic variable. Okay, volume. So volume will be always volume of that system, right? So it is also a macroscopic variable. Pressure also, it's pressure of the system. It's not pressure of okay one atom, two atoms, okay, or five molecules. It is pressure of the system. Mass also, it's the macroscopic property, right? So that's the difference between microscopic and macroscopic. This is clear. After that, there are some intensive and extensive properties, intensive and extensive variables. So these macroscopic properties of the system, they are known as thermodynamic variables. Okay. They are known as what? Thermodynamic variables. So there are some intensive variables, there are some extensive variables. So what do you mean by intensive and extensive? Intensive means if you change the size of the system, then that variable is not going to change. Okay, that means the variable does not depend on the size of the system. Okay, so which are the things which depend on the size of the system? Mass will depend, right? Volume will depend. So mass and volume are the extensive properties or extensive variables, and the density, the pressure, the temperature, okay, they are intensive variables. Okay, this is clear. After that, there is next term, the internal energy of the system. What is internal energy? Internal energy is just sum of potential energy of the system and the kinetic energy of all particles within the system. Okay, so total kinetic energy of the system. So internal energy of the system is just sum of the potential energy and kinetic energy of all the molecules, or if there are atoms, all the atoms of the system. Okay, that's internal energy, right? So after that, next comes the zeroth law of thermodynamics. So why is it known as the zeroth law of thermodynamics? So these people like Carnot, okay, Joule, etc. Uh, they studied the properties of engine, right? And they came up with first law of thermodynamics, second law of thermodynamics, okay, and third law of thermodynamics, right? After that, they realized that there is very basic thing, okay, that they had missed, and that was proved later, much later, okay, but it's very basic thing, so they cannot call it fourth law of thermodynamics, okay, and that's why they named it as a zeroth law of thermodynamics. So what is that very basic thing? So the zeroth law of thermodynamics states that if two systems are in thermal equilibrium with the third system, then all three are in thermal equilibrium with each other. Okay, so two systems are in thermal equilibrium with the third system, then all three are in thermal equilibrium. So now you might say this is such a basic thing. How did they miss it? So this is just a statement, right? This is like a common sense. So these things were proved mathematically. Okay, mathematically means there is a branch of physics known as statistical mechanics. Okay, so uh, in statistical mechanics, what you do is you prove the laws of thermodynamics, okay, thermodynamic properties of systems and the laws by using the statistic, okay, statistics of the constituent particles. Okay, so this thing was proved much later, and that's why it was named zeroth law. So this is very basic thing. So now what does it mean? So for an example, we have system 1, system 2, system 3. These are three systems. Okay, and now there is a adiabatic wall between system 1 and system 2. So what does an adiabatic wall mean? It means that there cannot be a transfer of heat between the two systems. Okay, so these two systems are separated by adiabatic wall or adiabatic wall, whatever you prefer to call it. Adiabatic wall, okay, does not allow transfer of heat, right? Adiabatic wall does not allow the transfer of heat. Okay, so there is no heat exchange between system 1 and system 2. Okay, so for now we can say they are isolated. And here we have third system, which is in contact with first system as well as second system, and the wall that is separating the first and third and second and third, it is a diathermic wall or diathermal wall. So what does it mean? What will happen? Heat will get exchanged between 1 and 3 as well as between 2 and 3, right? So what will happen as a result of this? So right now we can just say that heat will get exchanged, okay, till the time the temperature of first and third and second and third becomes equal. Okay, so we don't know about what happens to the first and second, but we can say the temperature of first and third will be equal, because till the time temperature becomes equal, the heat will get transferred from hot system to cold system. Okay, so at some temperature, sorry, uh, at equilibrium, what will happen? The temperatures will become same, so there will be no more exchange of heat. Okay, even if there is a diathermic wall, there is no exchange of heat, because temperature of this body and temperature of this body has become equal. Similarly, temperature of this body and temperature of this body has become equal. Okay, so now what you do is, in order to check the zeroth law of thermodynamics, now you put a adiabatic wall here. So earlier there was a diathermic wall. Now you replace that with an adiabatic wall, and here what you do is you insert a diathermal diathermal wall or diathermic wall, and you remove the adiabatic wall. So now what you are doing? So you know that system 1 and 3 are in thermal equilibrium, system 2 and 3 they are in thermal equilibrium, but you don't know about 1 and 2. Okay, so now you have put a adiabatic wall here, a diathermic wall here. Okay, so you are allowing the exchange of heat between 1 and 2. So if there is an exchange of heat between 1 and 2, that means zeroth law of thermodynamics is not valid, right? But you will see that there is no exchange of heat between system 1 and system 2. Okay, so there won't be any exchange of heat between system 1 and system 2, even if there is a diathermic wall. Why? Because the zeroth law of thermodynamics says that they are in equilibrium. Okay, yes, no? Okay. So this is zeroth law of thermodynamics. After that, next, let's come to the first law of thermodynamics. So what is first law of thermodynamics? The first law of thermodynamics states that suppose you heat a system. Okay, what happens? That system will take that heat, that energy, and that energy will be utilized in increasing the internal energy and doing some work against the surrounding. Okay, so the statement of first law of thermodynamics is, suppose, okay, the first law of thermodynamics states that the heat supplied to a system is equal to the sum of work done by the system and change in the internal energy of the system. So you give some heat delta Q to this system. So what will happen as a result of this? Internal energy of the system will rise, and the system will do some work against the surrounding. Okay, so energy given is equal to what? Sum of the internal energy plus the work done against surrounding. This is the first law of thermodynamics. Okay, so now see, here you are supplying some heat to the system. What is the system? The system is a gas. Okay, this is a container. There is this gas inside this container. It's an ideal gas, meaning it will obey PV equals to nRT, right? So this is an ideal gas, and there is this piston, a massless, frictionless piston. Okay, so this piston is just kept like this. Okay, the piston is just kept like this. You're not pushing on it. Okay, you're not applying any excess pressure. There is some surrounding, so you might say there is air. Okay, you can say there is air, so that pressure on that piston will be equal to what? Air pressure, the atmospheric pressure. Okay, now you heat this system, right? You heat this system, so you are giving some energy. What will happen as a result of this? The molecules inside this system, they are heated, they got some energy. the temperature has increased. So their molecular activities will increase. What are molecular activities? They will move with higher velocities, right? So their kinetic energies are increased. And what what else happens? So what happens is these molecules now they exert some pressure on this piston. Okay, so they push this piston outwards. Okay, because their energy has increased, they want more space, right? So the volume of the system also increases. Okay, so one thing is the kinetic energy of these particles has increased. Okay, that is internal energy, increment in internal energy. And what extra thing is happening? So these molecules are pushing on this piston, so this piston is pushed outwards. That means the volume is increasing. Okay, so some work is done against the surrounding. Okay, because surrounding is exerting some pressure, okay, on the system, that is the atmospheric pressure, and system is exerting some opposite pressure from this side, and because of this opposite pressure some work is done. Okay, so the total energy is equal to what? The internal energy plus work done. Okay, so this thing is clear? Yes, no? Now how do we measure this work? How do we measure this work? So we know that the work done is equal to what? It is force multiplied by displacement. Okay, so if we consider small displacement, then all right. So you have some gas here, okay, and these molecules, gas molecules, they are exerting some force on this piston. So force is suppose F. So we know that pressure is equal to force upon area, right? So the force will be equal to what? Sorry, yeah, force will be equal to pressure multiplied by area. Okay, force is equal to pressure multiplied by area. So now what happens is this piston is pushed from this point to this point. Okay, so this much is displacement, suppose small displacement dx. So how much would be the work done? Let's call it dw. Dw will be equal to what? F dot dx, and that is equal to p into dA, sorry, p into a multiplied by dx. And what is a times dx? What is a times dx? Yeah, it is change in volume. It is only this much volume, right? This is the area, this is the volume. A times dx is change in volume. Okay, and therefore we can say the work done is equal to what? The work done is equal to p times dv, right? This is clear. Okay, so there is small work done. This is small work done when there is small displacement of the piston by dx. Okay, so this piston is now pushed, suppose from position A to position B. Then how will we find the total work done? So total work done would be just integral of p dv, right? It will be integral of p dv from initial volume, from some initial volume v1 to final volume v2. And now if I plot the graph between pressure and volume, okay, if I plot the graph between pressure and volume, suppose it looks like this. So now what will be this work done on this pressure volume graph? What will be this work done on this pressure volume graph? It is just equal to area under this graph, right? So just like earlier we had work done is equal to what? The area under force versus position graph. Okay, F and X graph. So here we have work done equals to integral of P dV instead of F dx. Okay, so it will be area under pressure volume curve. Okay, so this thing is clear, right? After that, in this formula, now when will this dw or delta w positive, when it will be negative? Can you tell me? Work done on the system is okay, but that depends. Okay, that depends. Okay, let me tell you. So, what is work done on the system and what is work done by the system? So, see, you have this piston, okay, and its surrounding is doing some work on the system, right? If surrounding is doing some work on the system, then here it is called as positive work, okay? So now the system will get compressed. This gas will get compressed, okay? So this is positive work. And if system is doing some work on the surrounding, then there will be some expansion. So this will be negative work, okay? So this is clear, right? But now see this formula, delta Q is equal to delta U plus delta W. Delta Q is equal to delta W plus delta U. In order to use this notation of positive and negative, we have to write it like this. Delta U is equal to delta Q minus delta W. You got it? Yes, no? Okay. See, for an example, I'm giving some 10 joule of heat, okay, to this system. And now what is happening? The internal energy of the system is increasing by 5 joules. Okay. Where is that remaining 5 going? No, no, I'm giving heat of 10 joules. So some 5 joule of internal energy. Okay. There is increment in internal energy which is equal to 5 joules. Okay. Now the remaining of energy is used by the system to do some work. Okay. So I can say 10 is equal to what? 5 plus 5. And I say this 10 is equal to 5 plus 5. So in this case, work done is also positive and delta U is also positive. Okay. And this is work done by the system. It is not work done on the system. Okay. So see, if you are using this formula, delta Q is equal to delta W plus delta U. Okay. Then see, delta Q is the heat given. The context matters. Okay. Delta Q is heat given to the system. Okay. Which is positive. Now, some part of it, you can say some part of it is used to do some work and some part of it is used to increase the internal energy. Then delta W is also positive, delta U is also positive. Okay, if delta W is work done by the system, then this is also positive. But now if you are taking what, delta U is equal to delta Q, and instead of negative, if I use positive sign here, okay, if I use a positive sign here, then okay, what is the increment in internal energy of the system? So it is equal to delta Q, that is the heat given, plus delta W, that is the work done by the surrounding on the system. Are you getting this? Yes, no? So if you are using formula like this, then this notation will be valid. Okay. So what I will do is, okay, see, I will tell you the method in which you will not get confused. So see, you are giving some heat, you are giving some heat to the system. Okay. Now whether delta W is positive or negative. So if work is done by the system, so system is taking that heat and doing some work over the surrounding, then we'll use formula like this. Okay, the textbook formula. So delta W will be positive in this case and it will be negative in this case. What this? Yes, no. Okay. So we'll use a formula, this formula only, not any other form. Okay, heat given is equal to what? Increment in energy plus work done. Right? Heat given, I'm giving some heat, part of it is used in increasing the internal energy, part of it is used by the system to do work against the surrounding. So if I use this formula and if system is doing some work over the surrounding, then I will call this work as positive. Okay. If volume of the system increases, then I will take this as positive in this formula. And if the volume of system decreases, I will take this as negative, because in this case the surrounding is doing some work, so work done by the system would be negative. Okay, so in this case different teachers have different methods. Okay, so I use this method, right? Some heat is given, part of it is used to increase the internal energy and part of it is used by the system to do work against the surrounding. So if system is doing work, then we'll consider work done as positive. And now that means volume of system increases, work done is positive. If volume of system decreases, then work done would be negative. This is clear? Okay, good. All right. So please remember this in this manner. Okay. So then next is thermodynamic processes. So we have a limited system, we have a gas, we have some heat burner. Okay. And we have suppose a thermometer, etc., etc. So what are the various things we can do with this system? With this system only. So what we can do is we can keep the temperature constant, or we can keep pressure constant, we can keep volume constant, etc., etc. So there are various processes, okay, that can be done. So there is an idealized process, thermodynamic process, which is known as quasi-static process. Okay, so what is a quasi-static process? So by definition it is an infinitely slow process. Okay, so here itself you can guess this is an idealization. This is not, this doesn't happen in practice. This is infinitely slow process in which the system remains in a thermal and mechanical equilibrium with the surrounding at all times. Okay, so from start to end of this process, what will happen? The system will remain in the thermodynamic equilibrium with the surrounding. Okay, so the temperature of the system will remain constant. Okay, right, the temperature of the system will remain constant. Then all the thermodynamic properties, you can say, they are not, they are in equilibrium with the surrounding. So this kind of a process is known as quasi static process, infinitely slow process. This thing is clear. So practically this thing is not possible. Okay, practically this thing is not possible, right? At all times the system cannot be in equilibrium with the surrounding. If it is so, nothing will happen. Okay, if it is so, if system is in equilibrium with the surrounding, what does it mean? The temperature of system, temperature of surrounding, it is equal. Okay, then there is no transfer of mass between system and surrounding. Okay, right, the chemical composition of system and surrounding will remain as it is. So if everything remains as it is, nothing will happen. Okay, all right, so this is an idealization. Okay, then let's come to an isothermal process. So what is an isothermal process? So its meaning is clear from the name itself. What is isothermal? Iso means it remains constant. Okay, it remains the same. Thermal means temperature. So in this process, the temperature of the system will remain constant. Okay, in this process, the temperature of the system will remain constant. So if temperature remains constant, what does it mean? So our system is an ideal gas. So it follows this law, PV equals to nRT, right? So if temperature is constant, that means P times V is constant. Okay, P times V is constant. Okay, so therefore, now what will happen? So if P times V is constant, okay, temperature is constant. That means internal energy of the system remains constant. Is this thing clear? Temperature is constant means internal energy of the system remains constant. Okay. So what happens to the heat given to the system then? What happens to the heat given? If internal energy remains constant, delta Q equals to delta W. Okay, or Q equals to W. Heat given completely is utilized in doing just work. Okay, against the surrounding. Okay, so how can you achieve this thing? How can you keep the temperature constant? Okay, so let me ask it to you in this way. Suppose I have diathermal wall between system and surrounding, and I have adiabatic wall. In which case, the process will be thermodynamic process. Sorry, which one? Isothermal process. In diathermic, why? In diathermic, what happens? There is heat is exchanged between system and surrounding. So see, here you have surrounding which is at a some temperature, which is at some temperature. Okay, you start with thermal equilibrium. That means temperature of the system and surrounding it is same. Okay, now you start heating this system up. What will happen? So surrounding is very big. Okay, surrounding is very big. Suppose there is air surrounding the system and there is a diathermic wall. So what will happen now? So you give some heat, temperature of the system it rises. Okay, but as soon as there is slight change in temperature, what happens? The heat flows from the system to the surrounding. Okay, such that temperature again comes back to what? Temperature of the surrounding. Okay, so when you give some heat, what will happen? It will push this piston, but without changing the temperature of the system, because you have diathermic walls between the system and surrounding. Right? This is clear. Okay, so there is no increment in temperature if you do this, if you separate the system and surrounding by a diathermic wall. Okay, so now we have seen PV equals to constant. So now if you differentiate this, what do you get? If PV is constant, you take differential of this. So you can write PdV. Okay, so first term as it is, take derivative of second term, differential of second term. So it is PdV plus take differential of first term dP into V. Okay, uh, and keep second term as it is. So differential of first term is dP, second term as it is, V as it is. So this is equal to 0. Okay, so therefore now you can move this dP into V on other side, it will be negative, and then you can take the ratio of dP by dV. Okay, so what is ratio of dP by dV? Change in pressure or change in volume. Okay, so now if you plot this thermodynamic process, which thermodynamic process? Isothermal process. Okay, if you plot PV curve for that, then you get a curve like this. Okay, you get a curve like this. And if you want slope of this PV curve, that slope of PV curve will be what? It will be minus P by V. Okay, so we get it from here. If we move this PdV on this side, it will be minus PdV. Okay, then move dV on this side. So you will get dP upon dV and take this V also on other side. So it will be minus P by V, right? So dP by dV, change in pressure, change over vertical axis divided by change over horizontal axis. That slope is equal to what? Minus P by V. And you can see that it's negative because see, as what happens, volume increases, pressure will decrease because pressure times volume is constant. Is this thing clear? So this kind of curve has a special name. It is known as an isotherm. Okay, this is for isothermal process, and this curve, the graph between pressure and volume, it is known as isotherm. Okay, now you will have various isotherms like this. So on this isotherm, temperature is constant. So let's suppose this is some 500 kelvins, or let's suppose this is 1000 kelvins. Okay, so suppose for 500 kelvins you will get another isotherm. Okay, it will be on this side or other side. It will be on this side, right? Yes, no, I'm sorry. Okay, so this is suppose at 500 kelvins. Okay. Then you have another one at 300 kelvins, so on and so forth. So corresponding to various temperatures, you can draw various isotherms. And what can you say about these isotherms? Will they intersect each other or they will not intersect each other? They will not intersect each other. Okay, isotherms will not intersect each other because you change the temperature slightly. Okay, suppose this is at 1000 Kelvin, you take at 900 kelvins or 950 kelvins, the curve will start here. Okay, and now if you move here, means that the temperature has changed to what? 1000 kelvins. Okay, so if you plot a graph at 950 kelvins, it will never intersect with 1000 kelvins. If you plot a graph at 999 kelvins, it will not intersect with 1000 kelvins because as you move onto that graph, what does it mean? Temperature has changed to 1000 kelvins. Okay, so this is property of isotherms. Two isotherms will never intersect each other. They are always parallel. This thing is clear. Okay, there might be questions based upon these minute small things. Okay, then the work done in an isothermal process. So we know work done is area under the PV curve. Okay, so suppose initial volume is Vi, final volume is Vf. Okay, then the work done is equal to what? Integral of PdV from Vi to Vf. And now if we substitute PV equals to constant in this one, so P can be replaced by what? PV equals to nRT. So P can be replaced by what? nRT by V. And if you just substitute that over here, what do you get? Integral of that thing, you can take nRT outside. Integral of 1 of V will be what? Log of V. So you get this formula. Okay, nRT log of Vf by Vi. Okay, so we have to remember this formula. This is clear. Okay, sorry. So these many things we have to remember for isothermal process. Okay. After that, next comes an adiabatic process. What is an adiabatic process? There is no exchange of heat between the system and the surrounding. Okay. So it is a process in which there is no exchange of heat between the system and surrounding. And now this is found, okay, and proof of this thing is not there in our syllabus, that in case of adiabatic process, PV raised to gamma is a constant. Okay. In case of an adiabatic process, PV raised to gamma is a constant. And what is this gamma? Gamma is the ratio of specific heat capacity at constant pressure. Okay, we have seen this in last chapter that Cp is equal to what? Specific heat capacity, molar specific heat capacity at constant pressure, and this is molar specific heat capacity at constant volume. Okay, so gamma is ratio of capital Cp to capital Cv. Okay, molar specific capacity at constant pressure to molar specific capacity at constant volume. Okay, and for the air, which is the most general of all systems, it is near about 1.4. Gamma is near about 1.4. Okay, so then if you look here, this is the graph of an adiabatic process. This is graph of an isothermal process. So the adiabatic process is steeper, sharper. Okay, so fall is sharper on the adiabatic process. Okay, so if this is an isothermal process, the adiabatic process will be like this. Okay, how can you distinguish between two graphs? This will be little bit, not little bit, much steeper actually compared to isothermal process. Okay, and then now work done is equal to what? Work done is equal to integral from V1 to V2 of PdV. Okay, so it will be equal to P2 V2 minus P1 V1 divided by 1 minus gamma. So here once again what we have to do is we can substitute for pressure using this formula. PV raised to gamma is a constant. Okay, and then we get P2 V2 minus P1 V1 divided by 1 minus gamma. Okay, this is one formula, and we can write it in terms of nRT. So it is nRT2 for P2 V2 minus nRT1 for P1 V1 divided by 1 minus gamma. The same formula actually, we just have written PV equals to nRT, right? This is clear. Okay, so here we have to remember these many things, and of course what will be the wall separating the system and surrounding in case of an adiabatic process? Will be isothermal diathermic wall or adiabatic wall? Adiabatic wall. So what does it mean? There is exchange, yeah, there is no exchange of heat between system and surrounding. And again, what does it mean if there is no exchange of heat between system and surrounding? Where is this work coming from? It is coming from internal energy. Okay, so if system is doing some work over the surrounding, what will happen? Its internal energy will decrease. Okay, because there is no heat intake, right? So it is using its internal energy to do some work. So there is some expansion. What will happen? Internal energy will decrease. So if internal energy decreases, that means system will cool down. Get it? And if surrounding is doing some work, what will happen? So surrounding is giving some energy in form of what? That work to the system. So the system will heat up. So now if this is an adiabatic process, okay, so there can be a question like this. In adiabatic expansion, the temperature of system, what happens to the temperature of system? So let me just make this point because this is important one. Okay, So in adiabatic expansion, the temperature of system, what happens? Increases or decreases? See, you have this formula, delta Q is equal to delta W plus what? Delta U. Okay, so this thing is 0. This thing is 0. Now you can move. So delta U is equal to what? Minus of delta W. Okay. So if delta W is positive, that means there is expansion. System is doing some work. So what happens to delta W? Change in internal energy. It becomes negative. Okay. If this is negative, what does it mean? If there is expansion, change in internal energy is negative. That means internal energy is decreasing. Right? So if internal energy is decreasing, means temperature, what happens to temperature? Decreases. Okay, this will be some constant times temperature. Okay, actually we'll see this in kinetic theory of gases. Okay, and little bit in this chapter also, that internal energy can be written as what? Internal energy is equal to R into T, some factor multiplied by R into T. Okay, so internal energy of system is directly proportional to temperature, or temperature is directly proportional to the internal energy. Okay, so internal energy decreases, means what happens? Temperature will decrease, right? So in adiabatic expansion, what happens? The temperature of system decreases. Okay, and in case of adiabatic compression, here what is happening? The surrounding is compressing the system. That means it is giving some energy to the system. So temperature will increase. Okay, the temperature of system increases. So surrounding is giving some energy, not in terms of heat, not in form of heat, but in form of the work that it is doing. It is compressing the system. So in order to compress, you have to give some energy, right? Where will that energy go? It will increase the internal energy of the system. That means what will happen? The temperature will increase. Is this thing clear? Okay. So please remember these points. Then next, let's come at isochoric process. What is isochoric process? So isochoric means volume is constant. So in isochoric process, the volume remains constant, so no work is done. Okay, and how can you plot? I mean, how will the graph between pressure and volume look like in case of isochoric process? Sorry, volume will remain constant. What can change then? Pressure can change, right? So this is pressure, this is, I'm sorry, this is pressure, this is volume. So volume remains constant. Okay, so take some volume, it remains constant as you change the pressure. So graph will look like this. Okay, the graph will look like this. Okay, so how much is work done here? Work done is 0, because there can't be any area under this kind of a curve. Okay, so in this case no work is done. What does it mean? That if you keep the pressure constant, then if you give some energy, all of it does what? It changes the internal energy of the system. Okay, that means what will happen? Only and only the temperature of the system will change. Okay, what will happen? Only the temperature of the system will change. Volume does not change. Okay, so all of it is utilized in changing the temperature of the system. Volume remains constant. Okay, this thing is clear. Okay. So now if you want to measure the specific heat capacity at a constant volume, that means which process are you dealing with? So which is the process in which we find out the specific heat capacity of the system at a constant volume? The isochloric process, right? Yes, no. We want to find out the specific heat capacity at constant volume, then it is the process in which this thing happens is an isochloric process. Okay. After that, next one is an isobaric process. So what is isobaric process? Bar means pressure. Okay, there is one unit of pressure also which is known as 1 bar. Okay, so isobar means what? The pressure remains constant. Okay, the pressure remains constant. The pressure is fixed. So work done by the gas in this case is given by what? If pressure is fixed, so work done is what? P times dV. Only volume is changing. Pressure remains constant. So it is just P times final volume minus initial volume. P times V2 minus V1. Okay, and that is Nr times T2 minus T1. Okay, so this thing is clear. Yes, no. How will this graph look like? It will be like this, a horizontal line. Okay, right? So here we can summarize all four processes in this graph. So this is isobaric process. Okay, this one is isobaric process where pressure remains constant. So volume increases but pressure does not change. Okay, this is an isochloric process. Okay, here the volume remains constant. As you change the pressure of the system, volume remains constant. Okay, then this is isothermal and this one is adiabatic process, right? This thing is clear. Yes, no. Okay, now now let us see some problems based upon these things. Okay, let us discuss some problems. Two cylinders A and B of equal capacity are connected to each other via a stopcock. Uh, A contains an ideal gas at standard temperature and pressure. B contains B is completely evacuated. Okay, the entire system is thermally insulated. The stopcock is suddenly opened. The process is, tell me. Okay, so something is given here. Entire system is thermally insulated. Then the system is thermally insulated. That means there is there any exchange of heat between system and surrounding? No exchange. So which process is this? It is adiabatic process, right? Exactly. Okay. Good. Let's move on to the next one. Thermodynamic processes are indicated in the following diagram. So these are the thermodynamic processes. Okay. Match the following. So process 1, process 2, process 3, process 4. This is from NEET 2017. Option A is adiabatic, option B isobaric, as option C isochoric, option D isothermal. Okay, tell me what is one? One is what? Yes, this is isochoric. One is isochoric. Where is 4? Okay, 4 is isobaric. Okay, 3 is isothermal. Right. And 2 is adiabatic. Okay. So now just see the option. Which one is correct? Which one is correct? One is isochoric. Okay. Yeah. So one is P. Okay. There are P is what? Isochoric. So P is C. Okay. P is C. Then 4 is what? S. S is what? Baric. So it is B. Okay. 4, that is S is B. And then what is 3? 3 is R. R is what? Thermal. So it is D. And Q is what? Q is 2. So it is adiabatic A. So which one of these is correct? P is C, Q is A, option A. R is D and S is B. Right. So option A. So very simple question, right? Straightforward actually. Okay. Let's see next one. An ideal gas is compressed to half its initial volume by means of several processes. Which of the processes results in the maximum work done on the gas? Tell me. You are compressing. Okay. An ideal gas is compressed to half its initial volume by means of several processes. Which of the following will result in the maximum work done on the gas? Will it be isochoric? Will it be isothermal? Will it be adiabatic? Or it will be isobaric? All right. So now we can discuss this question. An ideal gas is compressed by several processes. Okay. So in which one the work done will be maximum? Can you tell me now? No, actually it will be isobaric. Is isobaric there? Yes, it will be isobaric, no? Why so? Reason is, see, the work done is equal to the area under pressure to volume graph. Okay. So in isochoric there is no work done at all. There is no area under this graph. So if you take not iso, adiabatic, then work done is this much. Right, work done is this much. If you take isothermal, there is this much extra work done in isothermal because total work done will be this plus this. Okay. If you consider isobaric, then work done would be what? This will be work done. So which one is maximum? Isobaric. So that is asked, no? In which process the maximum work is done? So it is the isobaric process, right? Okay. This is clear? Yes, no? Okay, good. Then let's move on to next one. Which of the following relations does not give the equation of adiabatic process where terms have their usual meaning? Okay. So in which one of these it's not an adiabatic process? So this one is adiabatic, PV raised to gamma is a constant. This is adiabatic. What else is adiabatic? Now we need to check, right? So, okay. So PV raised to gamma is a constant, but we also know that PV equals to nRT. Okay. So I will replace pressure. What can I do here? P will be equal to what? nRT upon V. I will use this one. And V equals to nRT upon P. I will use this one. Why? Because in one of these you have P, you have TV, okay, and in one of these you have PT, right? So let's use P equals to nRT upon V. So if I use that, I get nRT upon V into V raised to gamma is a constant. Okay, I'm using first one. Okay, so V raised to gamma upon V gives me V raised to gamma minus 1, and N and R are constant, right? So this is constant. You have T multiplied by V raised to gamma minus 1 is a constant. T multiplied by V raised to gamma minus 1 is a constant. T multiplied by V raised to gamma minus 1 is a constant. You got this. Okay. Then let's use second one, second relation. So I have to substitute volume here. So I will get P multiplied by volume is what? nRT upon P. Okay. And this is raised to gamma. So what is this? In numerator you will have T raised to gamma, and in denominator you will have P raised to gamma. Okay. NR are constant. Okay. So in numerator you have T raised to gamma. So take this P raised to gamma in numerator, it will be minus gamma. So you will have P raised to 1 minus gamma. 1 is here and minus gamma is here. P raised to 1 minus gamma and T raised to gamma. T raised to gamma. Which one is this? The option A. So these three are correct. That means this will be the answer, right? This does not represent an adiabatic process. Is this thing clear? Okay. Question is actually simple. You just have to replace in one case pressure by nRT upon V. Why? Because that option is given in terms of temperature and volume. One option is given in terms of pressure and temperature. So that means here you have to replace volume by nRT upon P. Right? Okay, good. Let us see next one. An ideal gas goes from state A to state B via three different processes as indicated in the PV diagram. So this is the PV diagram. If Q1, Q2, Q3 indicate the heat absorbed by the gas along the three processes, and delta U1, delta U2, delta U3 indicate the change in internal energy along the three processes respectively, then, okay, tell me. Q1, Q2, Q3 represent the, okay, tell me what will happen. Okay, so see, actually we are going to see this topic that U is equal to something multiplied by temperature. Okay, so it is directly proportional to temperature. So what does it mean? So if you go from point A to point B, the U will only depend on the initial temperature and final temperature, right? So these kind of variables are known as state variables. Okay, so they depend only on the initial state and final state. Okay, so here you can say A has some pressure, volume, temperature, and B also has some pressure, volume, temperature. So now U is totally determined by the temperature. Okay, U is totally determined by temperature. Okay, and therefore, since U is totally determined by temperature, what can we say? That the change in U in all three paths will be equal. Yes, no. Okay, change in U along all three paths will be equal. So, okay, so there will be some change in U, change in internal energy along this path, along this path, along this path, and along all those paths, the change in U will be same. So option C and option D is not possible. Okay, because they are saying change in U is different. Okay, but change in U is same. So now it's same in option A and B. So which one of these is correct? Can you guess? Delta U does not depend on anything else. It doesn't depend on path. It depends only on temperature. So initial temperature and final temperature. Okay. The change in temperature will be fixed. So delta U is fixed. What else is there? So Q is equal to, I'm just calling it Q. It is equal to delta W plus delta U, because they are calling it Q. Heat given, they are calling it Q. So if delta U is same, what other factor is there which will determine Q? It will be work done. So if work done is more, Q will be more. If work done is less, Q will be less. So tell me, work done along these paths, these three paths, for which one it is maximum? It is maximum for 1. Okay, it is this much. For 2, work done would be this much. For 3, it is even lesser, this much only. Okay, it is area under PV graph. So Q1 will be greater because work done for 1 is greater compared to work done for 2, and compared for work done for 3, Q2 is greater. Sorry, W2 is greater. Okay, therefore Q1 will be greater than Q2, it will be greater than Q3. So it is option A only, right? So this thing is clear. Okay, good. Next one, if delta U and delta W represent the increase in internal energy and work done by system. Okay, this thing is important, by the system respectively in a thermodynamical process. Which of the following is true? Delta U is equal to minus delta W in an adiabatic process. Delta U is equal to delta W in isothermal process. Delta U is equal to delta W in an adiabatic process. Delta U is equal to minus delta W in an isothermal process. Tell me, we have seen this. So in case of adiabatic process, we'll write general equation delta Q is equal to delta U plus delta W, right? And this delta W is work done by system on the surrounding. This one is positive. Okay. Now, in case of adiabatic, what happens? Delta Q is 0, right? Therefore, delta U is equal to minus delta W. This is for adiabatic. Is this option there? Option A. So this one is correct, right? This is straightforward. Okay. In case of isothermal, what happens? What is 0 in case of isothermal? Delta U is 0. Temperature remains constant, no? Okay. Delta U is 0. Okay. For isothermal, delta U equals to 0. So delta Q is equal to delta W. Okay. But that thing is not there. There is no delta Q in options. Okay. It is option A only. Right. Let's see next one. In thermodynamic process, which of the following statements is not true? Which is not true? In an isochoric process, pressure remains constant. This is not true, right? Volume remains constant. Okay, so answer is this one, but let's check others also. Okay, option B, in an isothermal process, the temperature remains constant. Exactly, it remains constant. In an adiabatic process, PV raised to gamma is constant. This is also true. In an adiabatic process, the system is insulated from the surrounding. Okay, so actually this question has given you some points to remember, that these three are correct. Okay, you have to remember these, this and this, right? And then, okay, these are important points to be remembered. Okay, all right, so this is the answer. This is not true. Okay, let us see next one. We consider a thermodynamic system if delta U represents the increase in its internal energy and W the work done by the system. Which of the following statements is true? Tell me which one is true. This is repeated, right? Delta U equals to minus W in adiabatic process, right? Because delta Q is equal to 0, so delta U equals to minus W in case of an adiabatic process. This is correct. Okay. Next one, a sample of gas expands from volume V1 to V2. The amount of work done by gas is greatest when the expansion is. This is also repeated. Tell me, we have seen this. It is option D, right? Isobaric. Next one, an ideal gas undergoing adiabatic change has which of the following pressure temperature relationship? Okay, so we had just derived this. Tell me. EV raised to gamma is constant, but we want pressure temperature. So what do we have to do? Replace volume by PV equals to nRT, right? That means volume. We are asked about pressure and temperature, so we have to substitute for volume. So it is nRT by P. So substitute that, then what do you get? P multiplied by nRT by P raised to gamma is a constant, and that is P multiplied by, this will be P raised to minus gamma because it is in denominator. Okay, and nr is constant, we'll forget about that. T raised to gamma, this is constant, so P raised to 1 minus gamma. Okay, P raised to 1 minus gamma, T raised to gamma is a constant. Option B, right? Okay, let's see next one. Which of the following is not thermodynamic function? So enthalpy, work done, Gibbs energy, internal energy. So enthalpy and Gibbs energy, you don't see in physics. Maybe you see it in enthalpy, you see in chemistry, right? Okay. Gibbs energy, do you see? Helmholtz free energy, Gibbs free energy. It's not there. It is there. chemistry it's there. Okay. Anyways, but question is which of the following is not thermodynamic function? So enthalpy is, Gibbs free energy is, then internal energy is also is, work done is not, right? Okay, so straightforward answer. Even if you just look at the physics syllabus, which one is not thermodynamic function? Work done is not a thermodynamic function. Okay, what is thermodynamic function? Whose value will depend on the initial state of system and final state of system. It will not depend on the path. Work done definitely depends on the path. So it's not a thermodynamic function. This is clear? Okay. Next one. So if Cp and Cv denote the specific heat per unit mass of ideal gas of molecular weight m, then okay, this is Meyer's relation. We are going to see this. You know this already. Option which one? Okay, but okay, it is for capital Cp and Cv. Cp minus Cv equals to R, right? This is for, this is Meyer's relation for molar specific heat capacities. Okay. Then these are molar specific heat capacities. Now, if you wanted to write it in terms of specific heat capacity, what will be your relation? What? Yeah. So this is equal to what? Okay. So Cp is equal to small t. C, capital C is equal to, we had used relation S. Okay, they are calling it C, small c, right? C upon m, C upon mass. Okay, m upon, sorry, S upon m, right? We had seen this in last chapter. Okay, or in place of S they are using small c. That's it. Notation different. Okay, so it will be capital C small c upon m. So we can replace this by small c upon m. So this will be small cp by m minus, okay, this will be small cv by m, and it is equal to R. Right? Or did I do a mistake here? Okay, let me write it. Okay, so small c is equal to q upon delta q by delta t. And here you will have m. And what is capital C? Capital C is equal to delta Q per unit number of moles per unit delta T. Now if you take 1 mole, so N will become 1. So capital C is delta Q by delta T, and small c is equal to delta Q upon M delta T. Right, no mistake, this is correct. Okay, so yeah, you can move that M on other side, so you will get Cp minus Cv is equal to Mr. Option D. Right, this is clear. Okay, all right, let's see next one. First law of thermodynamics is consequence of conservation of. Okay, so we are giving some energy, some of it increases internal energy, some of it does some work. What is this thing actually? This is just law of conservation of energy. Okay, you are using that energy to do some work and to increase the internal energy. So that energy is not being created or destroyed, just changed from one form to another form. Heat energy is changed to internal energy plus work, right? So this is just law of conservation of energy. Okay, right. So first law is just law of conservation of energy. Next one, 110 joule of heat is added to gaseous system whose internal energy is 40 joule. Then the amount of external work done is. Tell me. This is very straightforward. Delta Q is equal to delta U plus delta W. Delta Q is 110. It's equal to internal energy. Because internal energy is 40 joules, then amount of external work is what? So it is just move it on other side. 110 minus 40, 70, right? Okay. Next one. This was long back from 1993. So I don't expect this thing. Okay, just a subtraction. Anyways, let's see next one. The internal energy change in the system that has absorbed 2 kilocalorie of heat and done 500 joule of work is. Tell me. Here at least you have to do some multiplication. Okay, so delta Q is what? It is 2 kilocalorie. And what is conversion factor between calorie to joule? 1 calorie equals to 4.2. Sorry, 4.2 joules, right? This kilocalorie means 10 raised to 3. So this is equal to 2 multiplied by 4.2 multiplied by 10 raised to 3. Okay, it is 4.18, but for simplicity we'll take 4.2 only. So this is 8.4 into 10 raised to 3, 8,400, right? 8,400. And work done is 500. So this is equal to delta U plus delta W. Move delta W on other side. So delta U will be, okay, this thing minus delta W, which is 500. 7,900. Option C, right? Okay. Next one, a system is taken from state A to state C by two paths, ADC and ABC, ABC as shown in the figure. Okay. The internal energy at A is UA equals to 10 joule. Along the path ADC, okay. Along the path ADC, the amount of heat absorbed dq1 is equal to 50 joule, and work obtained dw1 is 20 joule. Whereas along the path ABC, this is ABC, the heat absorbed dq2 is 36 joule. The amount of work done along the path ABC is. Okay, all right. So tell me, what can we do? Internal energy at A is given. U at A is equal to what? 10 joules. Okay. Then take this path ADC. So what is given? dq1 is given and work done is given. That means we can find out change in internal energy, right? So dq1 is equal to du1 plus dw1. Okay, dq1 is 50, dw1 is 20. So that means du1 is what? 30. So this is along this path. Okay, so energy of this point is given, energy of point A is given. That means what will be energy of point C? du1 is positive. That means you are adding some energy. Okay, how much was earlier? 10, how much are you adding? 30. So how much will be the energy of point C? 40 joules, right? Okay. Then we can say dq2 is equal to du2 plus dw2. All right, but we don't want energy of point C, okay? But we can find it this way. Then dq2 is given. This is 36. Now what can we say about this thing? du2 will be 30 because it does not depend on path. It only depends on initial and final temperature. Okay. So for point A and point C, initial and final temperature will be same. Okay. This 36 is equal to 30 plus dw2. So what is dw2 then? 6, right? The option D. This is clear. Good. Let's see next one. A sample of 0.1 gram of water at 100 degrees Celsius and normal pressure. So this is normal pressure. Requires 54 calorie of heat energy to convert to steam at 100 degrees Celsius. So 0.1 gram of water is getting converted to steam. If volume of system produced, if the volume of the system produced is 167.11 cubic centimeter, cc means cubic centimeter. Okay. The change in the internal energy of sample is okay. Okay. Let's use, because some energy is given, heat is given, and some work is done. How much is change in internal energy? So delta U is equal to what? Delta Q minus delta W, right? I have just taken delta W on other side. Okay. We want change in internal energy. So this is 54 calorie. That means 54 multiplied by 4.2 in joules. And work done is how much? It is P delta V. Okay. P multiplied by V2 minus V1, right? So this thing we have to multiply 54 times 4. 54 times 4 is how much? 216. Right. 50 times 4 is 200. 4 times 4 is 16. 216. Okay. And 0.2. So 54 times 2 is how much? 108. So it will be 10.8. Okay. 0.2. Point after one digit. Right. So it will be 226.8. This is 226.8 minus. Pressure is how much? 1.013. We can just consider it is 1 multiplied by 10 raised to 5. Okay, no need to consider this thing. Okay, 1.013 because uh, we don't have time. Okay, V2. So how much is volume? Final volume 167. Okay, 167.1 cc. So 1 centimeter is what? 10 raised to minus 2 meters. We have centimeter cube, so it will be 10 raised to minus 6. Okay, this is V2. And how much would be the initial volume? Actually, it will be negligible because it is just zero point 0.1 gram of water, but still, okay, it is 0.1 multiplied by 10 raised to minus 3 multiplied by what? So this is, I have just converted into kilogram, right? Gram to kilogram. And then on top of that, you have what? This is the mass. And okay, how much would be volume? You have this relation, mass is equal to, sorry, density is equal to mass upon volume. Okay, so then you move volume on this side, density on this side. So how much is density? It's 10 raised to 3. So this will be actually negligible, right? Okay, we can neglect this. So 10 raised to minus 3, 10 raised to minus 3. Okay. Okay, so this is just equal to what? 226.8 minus 167 multiplied by 10 raised to 5 and minus 6. So it's 10 raised to minus 1. So it is 16.7. 226.8 minus 16.7. How much is this? 210.1, right? Close to that. Okay, so it is option B. Yes, no. This is clear. Okay. Why is the discrepancy there? Why the answer is different? Because we considered 1 calorie is equal to 4.2 joules. Okay. Actually, it is 4.18, not 4.2. That's why. Okay. So let's move on to the next topic, that is the molar specific heat capacity. So we already know what is molar specific heat capacity. It is amount of heat consumed or absorbed by a body per mole of body per degree rise in temperature. Okay. So what is molar specific heat capacity? Oh, I directly wrote isothermal process. Okay. Anyways, that doesn't matter. So what is molar specific heat capacity? It is amount of heat absorbed by a body per mole per degree rise in temperature, or you can say per Kelvin rise in temperature, right? So amount of heat absorbed by a body divided by number of moles divided by what? The change in temperature, that is specific heat. Now if we think of an isothermal process, so how much is change in temperature in isothermal thermal process? It is 0. So that means the denominator will become 0, right, for an isothermal process. So heat is absorbed, but there is no change in temperature. Okay. So the specific heat capacity of an isothermal process is what? It is infinity. Okay. Specific heat capacity of an isothermal process is infinity, right? Then next is adiabatic process. So in adiabatic process, there is change in temperature, but there is no heat absorbed, right? Adiabatic process is the process where the system and surrounding, they are isolated from each other. So there is no exchange of heat. So there is no change in heat, right? So heat is absorbed or it is given out, but there might be some change in temperature. So denominator is not 0, but numerator is 0. So here specific heat capacity is equal to what? 0. Okay, so this is important thing. For isothermal process, specific heat capacity is infinity. For molar specific heat capacity is infinity. For adiabatic process, it is equal to 0. Okay. Not only molar, actually any specific heat capacity, just heat capacity, it is also infinity for isothermal process and 0 for the adiabatic process. Is this thing clear? Okay. After that, next is isochoric process. So what happens in case of isochoric process? There is no change in volume, right? There is no change in volume. So specific heat capacity, molar specific heat capacity, we know it is delta Q divided by N, the number of moles, divided by delta T, right? And what is delta Q? So it is delta U plus delta W, okay? But since volume is constant, delta W is equal to 0. Delta W is 0, okay? And that's why PV is equal to what? Delta U divided by N delta T, okay? So specific heat capacity of an isochoric process is just equal to what? Change in internal energy of the system, because all the heat is utilized in changing what? The internal energy of the system. Okay. So change in internal energy of the system divided by number of moles divided by change in temperature. Okay. And therefore you can find out the change in internal energy of a system in an isochoric process. It is given by what? N times Cv delta T. This is clear? Alright. After that, let's come to isobaric process. So what happens in isobaric process? Pressure remains constant, right? So Cp will be equal to what? Same formula, delta Q divided by N divided by delta T, right? Divided by N delta T. So delta Q is equal to delta U plus delta W, okay? And then we can write delta U as N times Cv delta T. We just found it, right? Delta U is equal to N times Cv into delta T. We can substitute it here, okay? And then uh, we can write delta W. So what is delta W? It is delta W is P multiplied by V2 minus V1, okay? And right, pressure is constant, so it is P multiplied by just change in volume. Okay, that's work done because pressure is constant. So it is pressure multiplied by final volume minus pressure multiplied by initial volume. So now we can write PV equals to nRT, and from that we get it is just equal to N multiplied by R multiplied by delta T. Okay, so that is the work done in isobaric process. Okay. So then what you can do is you can find out relation between Cp and Cv. So what is the relation? So now you move this n times delta T on that side, then n delta T, you can cancel it out. So you get Cp equals to Cv plus R, or Cp minus Cv is equal to R. So the difference between the molar specific heat capacities at constant pressure and constant volume is equal to R. Okay, so this is known as Meyer's relation. This is famous. You might have studied this in chemistry also. Okay, after that, so we have to remember this thing. After that, we can find out the heat absorbed. So what will be heat absorbed in case of an isobaric process? It is just equal to, so here heat absorbed will be equal to Cp multiplied by N times delta T. This thing is clear? Yes, no? All right. So after that, now let's suppose we have an ideal monoatomic gas. Ideal monoatomic gas. So for an ideal monoatomic gas, we have to remember this thing, that Cv is equal to 3 by 2 R. Okay. So now there is a theorem which we'll study in next chapter actually. Okay. So the energy possessed per degree of freedom is equal to half of R per mole. Okay. So now see, okay, I will not tell the theorem right now. We'll just memorize it. Okay, for now. So for ideal monoatomic gas, just remember that Cv is equal to 3 by 2 R, right? So we'll see the reason behind this in the next chapter. Okay. So what will be Cp? So Cp is equal to what? 5 by 2 R. It is just Cv plus R. Okay. And what will be gamma? So gamma is equal to Cp upon Cv, and that is equal to what? 5 by 3. This is for ideal monoatomic gas. Okay. Now most of the times it is given what is Cp or Cv. If it's not given, we have to remember this thing because it's there in next chapter. Okay. Then next is ideal diatomic gas. So for an ideal diatomic gas, Cp is equal to what? Sorry, Cv is equal to 5 by 2 R. So what will be Cp? Cp is equal to then 7 by 2 R. Okay, and therefore what is gamma? So gamma is 7 by 5, okay, which is equal to 1.4, right? So for ideal monoatomic gas, gamma is equal to 5 by 3, and for ideal diatomic gas, it is equal to 7 by 5, that's equal to what? 1.4. And as I said in last lecture, for air, it is equal to 1.4. Why? Because air is diatomic mostly. Okay. So what are the constituents of air? It is nitrogen, which is N2, right? Then oxygen, O2, then hydrogen, H2, right? So most of the gases are in diatomic form, and there are some inert gases which are in monoatomic form, but they are very rare. So approximately we can say that the specific heat, specific heat capacity of air at constant volume, it is equal to what? 5 by 2 R. Okay, and at constant pressure it is equal to 7 by 2 R, and therefore gamma is equal to what? 7 by 5, that's equal to 1.4. Is this thing clear? The reason we'll see in the next chapter. Okay, all right. So after that, let's talk about a reversible and irreversible process. So what is a reversible process? What is an irreversible process? So what is reversible process? A process which can be reversed, right? So now suppose initially you had P1, the pressure of the system, volume was V1 and its temperature was T1. And now you go from this configuration P1, V1, T1 to some other configuration P2, V2, T2. Okay, right? So suppose I plot the pressure volume graph and I indicate the temperature also. So suppose the graph looks something like this. Oh, sorry. The graph looks something like this, suppose. Okay, so this one is corresponding to some pressure P1, some volume V1 at temperature T1. Then I go from this configuration of system A to the configuration B. So here pressure is suppose P1, sorry P2, volume is V2 and temperature is T2. Okay. So now what is an irreversible process? So I am going from this configuration P1, V1, T1 to P2, V2, T2. Now I will come back from B to A. We can always do that. Okay. We can always do this thing, that we can come back from this configuration to this configuration. But now while doing this, if there is no change in the surrounding, okay, so this is actually state of system plus surrounding, so there is no change in the universe, remaining universe, we can say, then we can say that this is a reversible process. This is completely reversible process. So what does it mean that there is no change in the universe? So while doing this thing, we shouldn't have to take some heat or some energy from the universe or give away some energy. Is this thing clear? But there should be no dissipation of heat. Okay, there should be no dissipation of heat from system plus surrounding to the remaining universe. Okay, so see, then what would be a reversible process? A reversible process is a thermodynamic process which can be turned back, okay, to the original state. I mean, in which system and surrounding will come back to the original state, but there will be no change anywhere in the universe, remaining universe. Okay, so now it means that the system and surrounding, they must be in equilibrium at all stages, right? System and surrounding, they must be in equilibrium. Okay, then only you can revert it back. Okay, so this process will happen infinitely slowly. So it is a quasi-static process. Okay, this is a quasi-static process. and there is no heat dissipated. Why? Because if there is some heat dissipated, then we'll need that energy, that much amount of extra energy, okay, to turn back the system from the final state to the initial state, to the original state, right? So this is an idealized process actually. This thing will not happen. This thing will not happen in practice. So in practice, all processes are irreversible, okay? Or at max, you can say approximately reversible, okay, not completely reversible. Why? Because as we discussed in last class, the quasi-static process is an approximation, okay? So some examples can be given. A quasi-static, any quasi-static process is a reversible process. So quasi-static isothermal expansion or compression of an ideal gas, then quasi-static adiabatic expansion or compression of ideal gas. These are some examples of reversible processes. So is this thing clear? Yes, no, or there is any doubt? Okay. So now for an example, so why most of the processes will not be reversible? For an example, now you take uh, some gas, it is confined to one corner of the room. Okay. Now suppose it is confined in a container in one corner of the room. Now there is a tap, okay, which you can open. You open that tap, so what will happen? Gas will spread out, okay, and it will occupy the room. Now while doing this, there will be some dissipation of heat, okay. So now this process cannot be reversed back. Why? There is no chance that all of a sudden all these molecules, gas molecules, which are wandering in random directions, they will reverse their path and they will come back and they will get compressed inside that container, which is located at one corner of the room, right? So gas which is sprayed out in a room, it will not come back, okay, and it will by itself, it will not get compressed to one corner of the room, right? Okay. So most of the processes are they are like this. They cannot be reversed. Okay. So so now what is an irreversible process? Most of the processes as we discussed are irreversible because there is some dissipation of energy, okay, either in the form of heat or some other forms. Okay. So now process is irreversible if it is fast. So this thing is fast, right? So expansion of gas, free expansion of gas, it is fast. It cannot be reverted. Then there is heat dissipation due to friction, viscosity, okay, a collision between particles of air, etc., etc. So there are various factors due to which some energy is lost, okay, and if you want to restore the system back to its original form, then you will have to supply some energy. That means you are making some change in the universe because you are taking some energy from the universe, okay. So then what is an irreversible process? One example I gave to you right now, okay. Then transfer of heat from hot body to cold body, this is irreversible process. So if heat gets transferred from hot to cold body, it cannot be reverted, okay. The reverse flow, it is not possible at all because the heat always flows from higher temperature to lower temperature, okay. Then diffusion of gas. So what is diffusion of gas? So for an example, you have some spray in a bottle, okay, and you spray it, okay. So some perfume is there, you spray it, then what happens? So that perfume is in the form of some molecules, right? So those molecules of the gas which was compressed inside that spray bottle, okay, they emerge out of the orifice of the bottle and now they sprayed. So while spreading, what happens? There are a lot of collisions between these molecules and the other gas molecules, the air molecules. Okay, and due to these random collisions, they spread in random directions. So this process is known as diffusion. Okay, so now in this diffusion process, now there is no chance that these molecules which have collided with n number of particles and have spread in n random directions. Okay, so there is no chance that these molecules will come back. They will collide back to the same molecules. Okay, and again they will come back to the spray bottle, right? So this is also an irreversible process. So is this thing clear? Okay, so if some heat is lost, if some energy is lost, process is irreversible. Okay, and actually all the processes are irreversible. For an example, you take, suppose there is some dam. Okay, and it is up the hill. Now you release water from that dam. Okay, so you might have seen waterfall. So that water falls down, right? So while falling down, what happens? There is some change in energy. Okay, so this process, our common sense will tell us that this is also not a reversible process, right? You can take any example actually, and you will find that the process is irreversible. Okay, so now there is a process known as cyclic process. What is cyclic process? Its system comes back to its original form. Okay, what is cyclic process? So in cyclic process, the system will come back. Oh, what happened? In cyclic process, what will happen? The system will come back to its original form, its original configuration. So suppose we consider the pressure volume graph of some system, and suppose the system has configuration A. That means it has got some pressure, some volume, some temperature, some internal energy, etc., etc. Now it goes from this configuration A to some other configuration. So for an example, it goes from here till here. So this is suppose B. Okay, this is B. Then after B, again it goes to some other point. Let's call it C. Okay. And then from C, it comes back to A. Okay. So this is a cycle. This is a cycle A, B, C, A. So this kind of process, this is actually combination of n processes, right? This is an isobaric process. Okay, here volume is not changing. This one is an isobaric process, right? So this process has not got any name. Okay, so here the pressure and volume is changing, both are changing, but they are not following uh, any pattern, like they are not I'm sorry, so this process is not isochoric, isobaric, or isothermal, etc., etc. Okay, but system comes back from C to the original configuration. So this kind of process, which is actually sum of n processes, it is known as a cyclic process. Okay, so this is known as what? A cyclic process. So now what will happen in case of cyclic process? So how much would be the change in internal energy? Can you tell me? What will be change in internal energy of the system in case of cyclic process? It is equal to 0, right? Because we had seen the internal energy of the system depends only on what? The initial configuration or initial state and final state. Okay, so suppose you have initial state P1, V1, T1, right? and you have final state P2 V2 T2, then the internal energy will only depend upon what? T1 and T2. So if system goes along this cyclic path and it comes back to A, then what will happen? There is no change in temperature. If there is no change in temperature, that means there is no change in internal energy. Is this thing clear? Okay. So now change in internal energy in case of a cyclic process would be equal to 0. Okay, so delta U is equal to 0 for a cyclic process. Okay, and how much would be the work done, or how much would be the heat absorbed or given out? Yeah. So work done is equal to area under the graph, and heat absorbed or heat released by the system is also equal to area under the graph. Because what? Because of what? Delta U is equal to 0. There is no change in internal energy of the system. So what is changing? Only one thing is changing, that is the work done. Okay. So there will be some work done which will be equal to area under the curve. Okay. So area under PV curve, and what is heat absorbed or heat, I'm sorry, how much is heat absorbed or heat given out? Is equal to work done. That is equal to what? Area under the curve. So this thing is clear. Okay. So now let us see some more problems based upon the thermodynamic processes. Okay. So yesterday we saw some simple problems. Oh, that doesn't mean these problems would be difficult. Okay. Let's see some more problems. That's it. Okay. So 1 mole of ideal diatomic gas. So this is diatomic. Once they say ideal diatomic gas, which thing should come to your mind? Cv equals to 5 by 2, Cp is equal to 7 by 2 times R, and gamma is equal to what? 7 by 5. It's equal to 1.4. Good. Okay. So then it undergoes a transition from A to B along a path AB. This path is given as shown in the figure. The change in internal energy of the gas during this transition is. So tell me. Now we know that change in internal energy of a system is equal to what? It is equal to Cp, sorry, n times PV multiplied by delta T, right? Okay. So what is relation of work done with delta T? So this is an ideal diatomic gas. So you can say PV equals to nRT, right? So P1 V1 minus P2 V2 will be equal to what? N times delta T. Okay. So this will be equal to what? What is N? It is 1 mole. How much is Cv? Cv will be equal to what? This is ideal diatomic gas. So it is pi by 2 R. Okay. And how much would be delta T? So find P1 V1 minus P2 V2. Actually P2 V2 minus P1 V1. Right. So will be P2 V2 minus P1 V1 divided by, so PV equals to nRT divided by nR it will be. Got it? Yes, no? Okay. Or see, PV equals to what? nRT Okay, so P1 V1 will be equal to NR times T1. P2 V2 will be equal to NR T2. Okay, so P2 V2 minus P1 V1 will be equal to what? P2 V2 minus P1 V1 will be equal to NR T2 minus T1, that is delta T. Okay, so we want change in energy which is equal to N times of CV into delta T, right? Change in internal energy, we have studied this formula, it is N times of CV into delta T. What is CV? CV is equal to 5 by 2 R. Okay, so here now what will be delta T therefore? So this is delta T, it is P2 V2 minus P1 V1 divided by NR. Take NR on other side, right? Is this thing clear? Okay. So then this will be equal to what? RR will get cancelled, N is equal to just 1. So what is P2 and V2? So this is P2 and V2. P2 is equal to 2, V2 is equal to 6, right? So you have 5 by 2 multiplied by 2 multiplied by 6. But what are the units? This is kilopascal and this is in meter cube. So we have to multiply it by 10 raised to 3. Okay, because pressure is in kilopascals. Okay, minus you have P1 V1. So P1 V1 is 5 into 10 raised to 3 multiplied by 4. So this is 5 multiplied by 10 raised to 3. This is the pressure. Volume is how much? It is 4. Okay. So you can take 10 raised to 3 common. It will be 12 minus 20. So how much is that? Minus 8. Right. 12 minus 20 is minus 8. Minus 8 divided by 2 is minus 4. And minus 4 times 5 is minus 20. Okay. So it is minus 20 multiplied by 10 raised to 3, and this is energy, the unit will be joules. Okay, right? So the answer is minus 20 kilojoules. Is this thing clear? Yes, no? Okay, good. Let's see next one. If the ratio of specific heat of a gas at constant pressure to that of constant volume is gamma, the change in internal energy of a mass of gas when the volume changes from V to 2V at constant pressure P is. Okay, this is simple. Tell me. Pressure is constant and you want change in internal energy. Ratio of specific heat capacity is given. It is gamma. What will this be? No, no. Gamma is Cp by Cv. That is true. Okay, so you can start. You can always start from here. Okay, change in internal energy is equal to what? It is equal to N times Cv into delta T. Okay, and then you have constant pressure. Okay, you have constant pressure P. So volume is changing from V to 2V. So how much is the work done here? P times V2 minus V1, right? So I can say work done is equal to P is constant, multiplied by delta V. So that is P multiplied by 2V minus V. Okay. So that is equal to what? It is equal to, yeah, PV. And what is this work done equal to? N times R multiplied by delta T, right? We have just solved this question. It's similar. Okay, it is N times R multiplied by delta T. Okay, so you will always have actually delta T equals to what? The work done divided by NR. Okay, so you have N times CV multiplied by what is delta T? So it is PV upon NR, right? So NN will get cancelled out, and then what do you get? So it is CV, okay, times PV upon R. So now what I can do is I can write R because in options I have gamma, gamma, gamma. Okay, so I can write R as, where will gamma come from? I can write R as Cp minus Cv, right? Yes, no? Okay. So I'm doing this looking at the options. So R is equal to Cp minus Cv, and in numerator you have Cv. Okay. And now take that Cv in denominator. So it will go in denominator of denominator. So this is equal to, you can say this is equal to PV upon Cp by Cv minus Cv by Cv, right? So what is that? PV upon gamma minus 1. Okay. Is everything clear? Yes, no? So this is the answer. PV upon gamma minus 1. So this will require some thinking. Okay. Okay. So is question difficult? Can you say this is difficult? Medium you can say, but it requires some thinking, right? All right. So see, you can always start if change in internal energy is asked. You can always start from here. Delta U is equal to what? N times Cv into delta T. And what do you have to find out? You just have to find out delta T. Okay. Once you find it out, delta T, then your answer will be there. Okay. All right. Let's see next one. 1 mole of an ideal gas requires 207 joule heat to rise the temperature by 10 Kelvin when heated at constant pressure. Again, it is constant pressure. Okay. If the same gas is heated at constant volume to raise the temperature by same 10 Kelvin, the heat required is. Okay. So in first case, it is heated at constant pressure. In second case, it is heated at constant volume. Okay. So tell me, you want the heat required. Okay, so let us think this way. Suppose delta Q is the heat required at constant volume. Sorry, constant pressure is suppose delta Q. Okay, so now you can write this as Cp multiplied by delta T, n times of Cp times delta T, right? Okay, but it is 1 mole of gas, that's why I wrote Cp times delta T. Okay, then now this delta Q can be written as what? Yeah, it can be written as U plus W. Okay, but we know that delta U is equal to what? N times Cv into delta T. So it is Cv into delta T in this case. Okay, so now see what is given. 1 mole of ideal gases, it requires 207 joule, okay, to rise by 10 Kelvin. So it is at constant pressure. So this is for the first case. For the second case, it requires some heat. How much is that? It's equal to delta U, because at constant volume, all the heat given to the system does what? It raises the internal energy of the system. So in the second case, delta Q at constant volume is equal to what? It is equal to just delta U. We know this, right? Okay. So after that, you want the heat required in second case. So you want to find out this thing. Okay. What is this thing? This is asked. Okay. So here you have Cp times delta T. Here you have Cv times delta T. So can we think of something? This thing is given. Delta Q at constant pressure is given. Okay. So can I say, okay, delta Q at constant pressure minus delta Q at constant volume. If I do that, why I'm doing that? Because I know the relation between Cp and Cv, right? If I subtract, I will get what? R. So it will be Cp minus Cv times delta T, right? Yes, no? I am just subtracting second equation from first one, okay? And this thing is given, this thing I want to find out. Okay, Cp is not given, Cv is not given, but what is that thing that we know? Cp minus Cv is equal to R. We know this, right? So this is equal to R times delta T. Delta T is also given, okay? So delta Q at constant pressure is 207 joules, and at constant volume you want to find out, okay? So R is how much? It is 8.3. 8.3 multiplied by change in temperature is 10. Okay. So just move this thing on. Just move this thing on this side, and delta Q at constant volume on other side. Okay. So our answer will be there. So let's move this thing on other side. So this is 83. So how much will be delta Q at constant volume? It will be 207 minus 83. 200 minus 80 is 120, 120, and 7 minus 3 is 4. So it is 124. Right? Is this thing clear? Okay. So we have done nothing. We have just written down whatever is given. Okay. So delta Q at constant pressure will be equal to what? It is given. Delta Q at constant pressure is given, and change in temperature is given. Okay. So now it's telling you to write down this equation, right? Because this thing is given, this thing is given. So what's connection between them? This equation is the connection. Delta Q at the constant pressure will be equal to N times Cp into delta T. Okay. Now you are asked what will be delta Q, the heat absorbed at constant volume. Okay. So we know that heat absorbed at constant volume, it is just equal to what? The change in internal energy, and that is equal to N times Cv delta T. Okay. And then just comparing the two equations, we get the answer. Is it clear? Okay. It will require some practice, but otherwise the questions are not that difficult. Okay. So this is a process, right? These are thermodynamic processes. So your answer will also follow a process. See this one, a monoatomic gas at pressure P having a volume V expands isothermally. Okay, it expands isothermally to volume 2V and then adiabatically to volume 16V. The final pressure of the gas is. Okay, tell me what can you do? You are given what the pressure and what is the initial volume. Then final volume is there. Okay, so you are asked what is final pressure. What will you need here? So see, first process is thermodynamics. I'm sorry. Okay, so here you have a monoatomic gas. Okay, once they say monoatomic, what should come to your mind? Cv, Cp, and gamma. Okay, monoatomic, diatomic, Cv, Cp, gamma. At pressure P, having a volume V expands isothermally to a volume 2V, then adiabatically to a volume 16V. Final pressure of the gas is, and gamma is also given, it's 5/3. Okay, even if it is not given, we know it. So see, initial pressure is given, initial volume is given. There are two processes. First is isothermal, second one is adiabatic, and final volume is given, final pressure is asked. So what should come to your mind? Initial pressure and volume is given, final volume is given. Right, that is for which process? For isothermal process. P1 V1 is equal to P2 V2. Right, exactly. So for isothermal process, you have P1 V1 equals to P2 V2. Okay, so initial pressure is P, initial volume is V, and at the end of this isothermal process, what is happening? The volume becomes 2V. Okay, so P2 multiplied by 2V. So how much will be pressure then? So volume becomes twice, pressure becomes half. Okay, or you can take that volume on this side, you get P2 equals to P by 2. Right, this is for isothermal process. Next, what do you have? You have, right, adiabatic process. What's the relation for adiabatic process? You know pressure now, you know volume. How much is pressure and volume at start of adiabatic process? Pressure is P2, volume is V2, right? So for adiabatic process, let's suppose starting pressure and volume, initial pressure and volume, okay? Initial configuration of system is P2 V2 and final is P3 V3. So what do you know about the adiabatic process? Tell me what remains constant or what is the relation between pressure volume? Okay, but we are given with pressure and volume. So PV raised to gamma is constant, right? So we can use PV raised to gamma is constant. So P2 V2 raised to gamma is equal to P3 V3 raised to I'm sorry, gamma. Okay. So P2 we know it is P by 2. V2 we know it is how much? 2V. Okay. So it is 2V raised to gamma is equal to P3 V3 raised to gamma. Okay, so we want P3. Let's move this V3 on this side because it is also given. How much is it at the end of adiabatic process? It is 16. Okay, 16 times V, right? So it is 2V upon 16V raised to gamma, I can say. Okay, I'm just taking this V3 raised to gamma on this side, and it is V2 raised to gamma upon V3 raised to gamma. So that is V2 by V3 raised to gamma. And this is P by 2. So this is equal to P3. And now we can substitute the value of gamma. So how much is gamma? It's 5 by 3. So let's substitute that. So what do we get? P by 2 multiplied by, this is 1 by 8 raised to 5 by 3. This is equal to P3, or P3 is equal to this thing. So tell me, what can we do? Exactly, exactly, right. So 1 by 8 can be written as what? It can be written as 1 by 2 raised to 3. Okay, so it will be 1 by 2 raised to 3. The 3 and 3 will get cancelled out. So it is 1 by 2 raised to 5. So how much is 1 by 2 raised to 5? What is 2 raised to 5? 32. Okay. So this is P by 2 multiplied by 1 by 2 raised to 5. It is P3. So this is 1 upon 32. So 32 times 2 is 64. So P3 is equal to what? It is equal to P upon 64. The answer. Okay. So option C. Got it? Yes, no? Okay. So now we'll solve many questions based upon thermodynamic processes because many questions have been asked. Okay. So at the beginning it might seem difficult, but once we complete this session, it won't be that difficult. Okay. So see, next one. During an adiabatic process, the pressure of a gas is found to be proportional to cube of its temperature. The ratio of Cp by Cv for gas is. So tell me, this is an adiabatic process. Tell me, what can we do? What can you say about adiabatic process? Delta Q is equal to 0. But delta Q equals to 0. Okay, it's good that it's coming to your mind. So what else happens? PV raised to gamma is constant, right? Okay. So because you are asked with Cp by Cv, okay, so this thing should come to our mind wherever Cp by Cv is there. What is Cp by Cv? Gamma is there. Okay, it's gamma. So it is PV raised to gamma equals to constant. This is a constant. Okay. So now what else is given? Pressure of gas is found to be proportional to cube of its temperature. Pressure is proportional to what? Cube of the temperature. Okay. So pressure is directly proportional to T cube, we can say, right? So we can substitute this here. So it will be some constant multiplied by T raised to 3. So I can replace pressure by temperature, right? Can I replace pressure by temperature? Of course we can replace, right? So we can say that this will be T raised to 3 multiplied by V raised to gamma, and this is a constant. I will call it C. Okay. Now we have temperature and you have V raised to gamma. This is constant. Okay. I have replaced pressure by some constant into T raised to 3. Okay. So because it is some constant times T raised to 3, it is still a constant. Yes, no? Okay. You want gamma. So can you find out gamma from this information? No, not yet. Right? We cannot find out gamma because temperature is not given. Okay. So what can we do then? What we can do is we can replace volume also. So we know PV equals to nRT. So I will say volume is equal to nRT upon P. Why am I doing this? It's because I know the relation between pressure and temperature. Okay, it is given. So I will remove volume also and I will convert everything in temperature. Okay, so see, you have nRT upon P, but P is proportional to what? T raised to 3. So here it will be nRT upon T raised to 3, some constant multiplied by T raised to 3. So volume is proportional to, you get T raised to minus 2. This is T raised to 1. Take the T raised to 3 in numerator, you will get T raised to minus 2, right? So I get volume is proportional to T raised to minus 2. Got it? Yes, no? All right. So then in place of volume, I will substitute what? T raised to minus 2. Okay. This is T multiplied by T raised to, sorry, T raised to 3 multiplied by T raised to minus 2 and raised to gamma. So it will become what? T raised to minus 2 gamma. And this is a constant. Okay. So now can you find out gamma? T raised to minus 2 gamma plus 3 is constant. Okay. If something is constant, then what can you say about that thing? What can you say about the derivative of that thing? If some function is constant, yes, derivative of this function with respect to t will be equal to 0. Okay. So I can say d by dt of this thing t raised to minus 2 gamma plus 3 is equal to 0 because this thing is constant. So therefore, take its derivative. It will be equal to minus 2 gamma plus 3 multiplied by t raised to what? Minus 2 gamma plus 3 minus 1, right? And this is equal to 0. Okay, n multiplied by t raised to n minus 1. Okay, but now you can divide this 0 by this thing. I mean, divide both sides by this term. What do you get? So see, this thing is not 0. Temperature is not 0. That means any power of temperature cannot be equal to 0. But on right hand side, you have 0. So what does it mean? Minus 2 gamma plus 3 is equal to 0. Right? You can do it this way, or you can say you divide both sides by this thing. Okay. So therefore, minus 2 gamma will be equal to 3. Okay. That, sorry, minus 2 gamma equals to minus 3. 2 gamma equals to 3. That means gamma is equal to what? 3 by 2. Okay. So see, gamma is asked. That's why we recalled that in adiabatic process, what happens? PV raised to gamma is a constant. Okay. Then since pressure is proportional to what? Temperature cube. We removed pressure and we put temperature cube. Okay. That is not sufficient because we have volume. Still we cannot find out relation between gamma. I'm sorry. What will be gamma? So what we do? We remove volume too. Okay. So we know relation between pressure and temperature, and we know relation between pressure and volume. PV equals to nRT. So we find out volume. right? And we substitute that here, and this thing is constant. Okay, we get this thing is constant. If this thing is constant, its derivative will be equal to what? 0. Okay, so this is actually, so process of thinking, we can say thermodynamic processes, the problems based upon thermodynamic processes, they require some thinking, but they are not difficult. Okay, is it clear? Yes, no? Now let's think on next problem. So a thermodynamic system is taken through the cycle ABCD, ABCD, okay, as shown in the figure. So actually this is a cycle, so they should have written it is ABCDA, right? Because system comes back to A. Heat rejected by the gas during the cycle is. So tell me. Now this is straightforward. Heat rejected is equal to what? Heat released equal to what? The work done. Right? We have just seen this. Okay, in the theory. So that is equal to, for a cyclic process. This is a cyclic process, right? Heat released is equal to work done, and that is just equal to area under the PV curve. Okay. So now in this case, see, when we go from A to B, let's find out work done when we move from A to B. So how much is pressure? Pressure is, yeah, constant. It's equal to P. Okay, here it is 2P. So pressure is P. How much is change in volume? V2 minus V1. Yeah, that is 2V. Okay, or VB minus VA, we can say. Okay, let me call it VB minus VA. So that is equal to 2 times V, because VB is 3V and VA is V. So this is equal to P multiplied by 2V or 2PV. Okay. Then what will be work done from B to C? Yes. Okay. No, there is no work done because volume is constant, right? Since volume is constant, there is no work done. So then you go from C to D. How much will be the work done? It will be equal to, now you are going in opposite sense. Okay. So pressure is 2P. Okay. VD minus VC, right? Final volume minus initial volume. So that is equal to 2P multiplied by, this is V minus 2V. V minus 3V, sorry. V minus 3V. So it is minus 2V. So how much is total work done then? Again, work done along this path is also 0 because volume is not changing. Total work done is WA to B plus WC to D. That is equal to 2PV plus how much? This is minus 4PV, and that is equal to minus 2PV. Okay, minus 4 plus 2 is minus 2. Okay, this much is work done. So how much is heat? Actually, work done is equal to heat absorbed. Okay, so I should have said this is heat absorbed. Okay, right? Heat taken by the system is equal to work done. Now they are asking about heat rejected or heat given out by the system. So if heat absorbed is this much, it means that heat absorbed is negative. It means that this much amount of heat is given out, given away by the system. Right? So what is the answer? 2 PV is the answer. Got it? Yes, no? Okay. So this is simple. And see, so you can directly say that this is a cyclic process. So I don't need to follow this thing. Just find out area under this curve. Okay. How much is that? It will be this area minus this area, right? Okay. So it is just area inside the square. Yes, no? I'm getting this. This is a cyclic process. So how much would be work done? Work done enclosed by that cycle. Okay, sorry, work done will be equal to area enclosed by that cycle. So area of a shape enclosed by this cycle. So it is equal to what? Area of this square. How much is that? So this side is 2p minus p. So it is equal to p. And this side is equal to 2v. So it is just p multiplied by 2v. 2 times pv. Okay, it is 2 times pv. So whether it will be positive or negative. If you go in this sense, in clockwise sense, it will be positive. In anti-clockwise sense, it will be negative. Right? Yes, no? This is clear? Okay. So you just need to find out this area. That's it. Okay. But you should understand what we are doing. That's why I explained it. Okay. All right. So then let's see next problem. A gas is taken through a cycle. So again, this is a cycle. A, B, C. A. As shown, what is net work done by the gas? Now, can you tell me? This is a cycle. So how much would be the net work done? It is just area of the shape enclosed by that cycle. Area of the shape made by that cycle, you can say. How much is the work done? So how much is this area? It is half of base into height. Okay. Half of base, half of, I will say, AC multiplied by BC. Okay. So that is equal to half of, what is AC? This is 2, this is 2, 4, 6, 8. So this is 7. Okay. So this much side will be how much? 7 minus 2. Right? Yes, no? Okay. And how much is this side? This is 6 minus 2. So how much is this? 4. Okay. But here we need to be careful because this side, its unit is 10 raised to minus 3. Okay. Volume is 10 raised to minus 3 meter cube. And for this side, it is 10 raised to 5. Okay. So for this side, it is 10 raised to minus 3. So I will say it is 5 multiplied by 10 raised to minus 3 multiplied by 4 multiplied by unit of this side. It is 10 raised to 5 pascals. Okay, so it is 10 raised to 5. So then what do we get? 4 by 2 is 2. 2 times 5 is 10. 10 multiplied by 10 raised to 5 minus 3 is 10 raised to 2. So that is 10 times 100. Okay, 1000 joules. Right? So 1000 joules is the answer. Got it? Yes, no? Okay. All right. Let's see next one. 1 mole of an ideal gas goes from initial state A to final state B via two processes. It first undergoes isothermal expansion from volume V to 3V and then its volume is reduced from 3V to V at a constant pressure. The correct PV diagram representing the two processes is, tell me. First one is what? Isothermal expansion, and then it goes from 3V to V at constant pressure. Okay, can you guess? I'm sorry. Okay. You said what? Option A. Okay. At first, what is happening? Volume is changing from V to 3V. Okay. And this is isothermal. So isothermal means graph will be like this. Okay. So it is like this in this one, and this one. Right. So this cannot be the answer. Okay. In this one and this one and this one, it is like what's there in isothermal process. Okay. But now volume is going from V to 3V. So this is V. So initial should be this, final should be this. So your arrow should be like this. So it's not there in first one. So first one is not possible. So arrow is like this. I mean from the initial volume to this final volume. Okay. Arrow should be like this. So it's there in this one and this one. So either it is B or it is D. Yeah. Okay. So it is D. Pressure is constant. Very good. So pressure is constant and volume is changed from 3V to V. So it is compressed from 3V to V using constant pressure. So pressure is constant. It's not constant here. It is changing. So in this case, pressure is constant. So it is answer. Option is answer D. Okay, very good. Okay, right. So this is simple. Okay, good. Let's see next one. The mass of diatomic gas gamma equals to, okay, sometimes it will be given, right? We have seen some questions. In some questions it was given, in some questions it's not given. We need to remember gamma is 1.4 at a pressure of 2 atmospheres is compressed adiabatically so that its temperature rises from 27 degrees Celsius to 927 degrees Celsius. The pressure of the gas in the final state is. So first of all, what will you do is you will change this temperature from degrees Celsius to kelvins. Why? Because in thermodynamics chapter, everywhere we use what? Only Kelvin scale, right? So how much is 27 degrees Celsius? T1 is 27 degrees Celsius. That is 300 Kelvin. 27 plus 273. And T2 is 927 degrees Celsius. That is how much? 927 plus 273. So it is 1200 Kelvins. Okay. Then what are you doing? So it's a diatomic gas. Gamma is given. Gamma is 1.4 and it is at pressure 2 atmospheres. It is compressed adiabatically so that the temperature rises from 27 to 927. Okay, so this is again an adiabatic process. So you can see lot of questions were based upon adiabatic process, right? Okay, so PV raised to gamma is constant. Yes, we want to substitute. Very good, very good. Right. See, I said no. Okay, once we solve some problems, you will start thinking because problems will be similar. Okay, so PV raised to gamma is constant. Okay, so P1 V1 raised to gamma will be equal to P2 V2 raised to gamma. And since we are given with temperature, we'll substitute for temperature instead of volume. Okay, so volume can be written as what? nRT upon P. Okay, and that is, yeah, that's it. So it is proportional to T by P. So we can say P1 and V1 is T1 by P1, right? Forget about NR, it will get cancelled. Okay, raised to gamma is equal to P2, and this will be T2 by P2 raised to gamma. Okay, so then this will be P1 raised to minus gamma, because P1 is in denominator. If you want to take it in numerator, it will be P1 raised to minus gamma, right? It is P1 raised to, already you have power 1 minus gamma. So it will be P1 raised to 1 minus gamma. T1 raised to gamma is equal to P2 raised to 1 minus gamma, T2 raised to gamma. And you want final pressure. So to move this temperature on this side, so you have P2 raised to 1 minus gamma is equal to T1 by T2 raised to gamma multiplied by P1 raised to 1 minus gamma. Okay, so what is this thing? T1 is 300, T2 is 1200. Raised to gamma, gamma is 1.4 multiplied by P1 raised to 1 minus gamma. All right, so this is 1 by 4, right? Let's write this, then let's think. P1 raised to 1 minus gamma. Okay, so yeah, we can do one more thing. So let's substitute this 1 minus gamma. It is 0.4, right? Okay, it will be minus 0.4 actually. P2 raised to, because gamma is what? It is 1.4. So this will be 1 minus 1.4. So that is minus 0.4, minus 0.4. Okay, so this will be 1 by 4 raised to 7 by 5 multiplied by P1 raised to minus 0.4. So what can we do now? So we have to remove this negative power. Okay, so then 0.4 can be written as what? We can write 0.4 as uh, 2 by 5, right? Yes, no? Okay. So if I write P2 raised to 0.4, okay, will be equal to, I'm sorry, this is P2 raised to minus 2 by 5, it will be equal to 1 by 4 raised to 7 by 5 multiplied by P1 raised to minus 2 by 5. Okay, so we can exchange P1 and P2, so that negative sign will go away, right? So if I move this, this is actually in denominator P1 raised to 2 by 5. Okay, so this thing is P2 raised to, sorry, this is 1 upon P2 raised to 2 by 5. So can we neglect 5 by 5? Of course we can do that. Okay, I will move this thing. I will write this as P1 by P2 raised to 2 by 5 is equal to 1 by 4 raised to 7 by 5. Okay, is it clear? This is actually 1 upon P1 raised to 2 by 5. So I have taken that P1 raised to 2 by 5 on other side. It goes to numerator. Okay, and this thing is P2 raised to 2 by minus 2 by 5 in numerator. So in denominator it will be P2 raised to 2 by 5. Okay, so then this 5 and 5 will go away. Okay, so then it's P1 by P2 square is equal to 1 by 4 raised to 7. Now let's take square root of this. So P1 by P2 will be equal to what? Square root of other side. It will be 1 by 2 raised to 7. Okay, and now we can uh, take what is 7th power of 2. Okay, 128. No, it will be 256, right? 2 times 2 is 4. Third power is, okay, third power is 8. Fourth power is 16. Fifth power will be 32. Okay, am I correct? Third is 8. Fourth is 16. Fifth is 32. Sixth is 64. And seventh would be 128. So answer would be 128, right? 1 by 128 is P1 by P2. Okay, P1 upon P2 is equal to 1 by 128. That means P2 is equal to 128 times P1. And how much is P1? P1 is 2. So it is 128 times 2, 256 atmosphere. Okay, this is the answer, option D. So lengthy question. I mean, calculation is lengthy, right? Okay, but anyways, this is how it has to be solved. Yes, it is lengthy. We can't do anything in this. Okay. Anyways, so this is clear, right? Okay. Process is clear. Actually, you thought about the process, so it is clear. Okay. Let's see next one. A monoatomic gas at pressure P1 and volume V1. Monoatomic. What should come to your mind? Cp, Cv, and gamma. Good. Cp, Cv, gamma. Okay. Compressed adiabatically to 1/8 of the original volume. What is the final pressure of the gas? So this is, yeah, P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Okay. So final pressure is asked. So P2 is just equal to what? See, what did I do? P1 V1 raised to gamma. Okay. So P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So P2 will be equal to what? P1 multiplied by V1 by V2 raised to gamma. How much is V2? 1/8. So P1 multiplied by 1/8 because V2 is 1 by 8. Okay, so V1 by V2 will be 8 actually. V2 is 1 by 8. Okay, V1 by 8 raised to gamma. So this ratio will be what? 8, right? So this is equal to P1 multiplied by 8 raised to gamma. What is gamma? This is monoatomic. Okay, so Cv is equal to 3 by 2 R. Cp is equal to I by 2 R. And gamma is equal to Cp by Cv, that is 5 by 3. So P2 is equal to P2 multiplied by 8 raised to 5 by 3. Yes, right, exactly. This is 2 raised to 3 multiplied by 5 by 3, and this 3 will get cancelled, and you have 2 raised to 5, that is 32. Oh, again, what am I doing? This is P1, right? So 32 times P1. This is the answer. Okay, good. So see, questions are becoming simple now. Okay. So let's see next one. 1 mole of an ideal gas at an initial temperature of T Kelvin. Initial temperature is T Kelvin. Does 6 joule of work adiabatically. Again, adiabatic process. If the ratio of specific heats of this gas at constant pressure and constant volume is 5 by 3, final temperature of the gas will be. Tell me. Initial temperature is given T1 is equal to T. Okay. And what is done? Work done is equal to what? 6 joule. Not 6 joule, 6 R. Okay. And it is adiabatic. The ratio of specific heat is given 5 by 3. Final temperature of the gas will be. This is by far the simplest question. What is work done in case of adiabatic process? Okay, but do you know the formula in terms of PV? This P2 V2 minus T1 V1 divided by 1 minus gamma, right? Or NR delta T, T2 minus T1 upon 1 minus gamma. Yes, no? Okay. So then work done is 6R. So this is 6R multiplied by 1 minus gamma is equal to NR times T2 minus T1. So RR gets cancelled. So the 6 minus 6 gamma, how much is gamma? 5 by 3 is equal to n times of T2 minus T1. N is 1, right? Okay. So it is 1. So T2 minus T1. So how much is this? This is 6 by 3 is 2. Okay. So you have 2 times 5, 10. This is minus 4. 6 minus 10 is minus 4 is T2 minus T1. T1 is T. So how much is T2? Therefore, T2 is equal to take the T on other side. So it is T minus 4 kelvins, right? So this is the answer. Okay. So this was direct formula based question. Okay. Yes, no. Right. So if you are doing PV raised to gamma in this one, okay, that will take longer time. All right. Let us see next one. An ideal gas at 27 degrees Celsius is compressed adiabatically to 8 by 27 of its original volume. The rise in temperature is. So can you see how many questions are based upon adiabatic process only? Okay. So instead of adiabatic process, I will say thermodynamic processes, because yesterday also we solved many questions. Today also we are solving many questions. So based upon thermodynamic processes, lot of questions have been asked. Okay. So mhm, okay. So an ideal gas at 27 degrees Celsius is compressed adiabatically to 8 by 27 of original volume. The rise in temperature is, yes, PV raised to gamma is constant, and we have to substitute for P. Very good. Volume is given. We have to substitute for P. What? nRT divided by V. Okay. So then we can write this as nRT upon V. So I will just say it is T by V multiplied by V raised to gamma is constant. So what is this thing then? T raised to 1, V raised to gamma minus 1, because this is V raised to 1 in denominator. V raised to gamma minus 1 is a constant. Okay. So T1 V1 raised to gamma minus 1 will be equal to T2 V2 raised to gamma minus 1. Okay. And therefore, what do we get? Mhm. We want T2, right? So T2 will be equal to V1 by V2 raised to gamma minus 1 multiplied by T1. So that is V1 by V2 is what? It is compressed. So this is V2 is 8 by 27 times V1. Okay. So it will be 27 by 8. V2 is equal to what? 8 by 27 times V1. So V1 by V2 is 27 by 8 raised to gamma minus 1. What is gamma? Pi by 3. Minus 1, this will be 2 by 3, right? Times T1. And T1 is 27 degrees Celsius. In kelvins, it will be what? 300. Good. So this will be, take cube root first. So 3 by 2 to the power 2, right? So, okay, cube root of 27 is 3, cube root of 8 is 2. So it is 3 by 2 to the power 2. So 3 by 2 raised to 2. That means it is 9 by 4 times 300. So 300 by 4 is 75. 3 by 4 is 0.75. 300 by 4 is 75. 75 times 9. Okay, 75 times 10 is 750 minus 75 is 75 times 9, right? So 625. 675. 675, right? Okay. This is rising. This is temperature, final temperature is 675 kelvins. And how much is rise? Right, 375 is the rise. Okay. So T2 minus T1 is the rise in temperature. That is 675 minus 300. So 375 kelvins. Good. This is rise in temperature. All right. Very good. Okay. Then let's see next one. A diatomic gas initially at 18 degrees Celsius is compressed area vertically to 1/8 of its original volume. The temperature of after compression will be. So just similar to the last problem. Okay. So shall I skip this? Okay. So I will include this in homework. Let's see next one. An adiabatic change. In an adiabatic change, the pressure and temperature of monoatomic gas are related as P proportional to T raised to C, where C equals. Okay, tell me. UV raised to gamma is constant. Then, very good. So V will be equal to what? T by P. Right. V will be equal to nRT by P. So you have P nRT by P raised to gamma. This is constant. So we can forget about nR. Okay. So this is P raised to what? 1 minus gamma. T raised to gamma is constant. Okay. So let's move this on other side. So P raised to, yes, P raised to 1 minus gamma will be equal to some constant times T raised to minus gamma. Oh, no, 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 no. This C and that C is different. So this is for constant, okay? This is not that C. Yes. Okay. So we have to find this power. P is proportional to T raised to some power. P will be equal to what? Some constant, okay, multiplied by T raised to minus gamma divided by 1 minus gamma, right? Okay, so this will be what? Minus gamma divided by 1 minus gamma. So gamma is what? This is monoatomic gas, so it's pi by 3. So it is, this is not that C, okay, this is some constant, okay, this is some constant, or instead of constant I will write suppose K to avoid confusion. So this is T raised to minus pi by 3 divided by 1 minus pi by 3. So that is minus 2 by 3, okay. So that will, minus minus will get cancelled, it is 5 by 2. Let's see next one. A thermodynamic system is taken from state A to B along ACB. Where is ACB? ACB, and is brought back to A along BDA. BDA as shown in the PV diagram. Okay, this is the PV diagram. The net work done during the complete cycle is given by area. So tell me, this is very, very simple. This system is taken from A to B and from B to A. Okay, ACB and then BDA. So which area will you consider? As we discussed, this is a cyclic process. So in case of cyclic process, you just have to consider the area. Work done will be just area enclosed by the cycle. So it is ACBDA, right? ACBDA, this area. Okay, so it is option C. Good. Then let's see this one. The thermodynamic process is shown in the figure. The pressure and volume corresponding to some points in the figure are PA, VA is given, PA, VA is given, PB is given, PB is given, and VD is given. In the process AB, in this process AB, 600 joule of work is added to the system, and process BC, 200 joule of heat is added to the system. The change in internal energy of the system in process AC will be, tell me. So internal energy only depends on starting point and end point, right? Okay. So then now when you go from B to C, okay, what will be the work done when you move from A to B? There is no work done. Okay. So you can say that delta Q is equal to what? Delta U plus delta W, right? So delta Q is equal to what? When you move from A to B plus B to C. So delta Q from A to B plus delta Q from B to C. How much is that? 600 and 200, right? 600, that much heat is added when you move from A to B, and when you move from B to C, 200 joule of extra heat is added. Okay, so that is equal to change in internal energy plus the work done. And how much is work done? There is no work done when you move from A to B. work done from A to B plus work done from B to C. And how much is work done from B to C? So pressure is constant. Okay. So this thing is 0. Work done from B to C is pressure is constant. It is equal to what? PA, PB only, not PA, multiplied by change in volume. So volume at C minus volume at B, VC minus VB. Okay, how much is that? So VC is given, not given, VD is given, which will be equal to VC, right? Yes, no. Okay. So VC and VD are equal. So it is 5 into 10 raised to minus 3 minus 2 into 10 raised to minus 3. So VC minus VB is equal to 5 minus 2 into 10 raised to minus 3. That is 3 into 10 raised to minus 3. Okay. So this is equal to 800 is equal to delta U plus PB. How much is PB? 8 into 10 raised to 4. 8 into 10 raised to 4 multiplied by 5 minus 2 is 3 multiplied by 10 raised to minus 3. How much is this? 8 3s are 24 and this is 4 minus 3, so it is 10 240, right? So let's move that 240 on other side. So we get delta U is equal to 800 minus 240. Okay. And that is equal to what? It will be 500 something, 560. Option A, right? This is clear? Yes, no? Okay. And see, we have found delta U when we move from A to B and B to C. That is when we move along this path. But we know that delta U does not depend on the path. So for the process AC also, the change in internal energy will be same, right? And that's why answer is same. Okay, 560 joules. So this thing is clear. All right. So we'll stop here and we'll move on to next part tomorrow. Second law of thermodynamics. So what does the second law of thermodynamics say? So there are various statements of second law of thermodynamics because various scientists and engineers, they worked on heat engines and refrigerators and they came up with their own statements, okay, which are equivalent actually. So there is statement by Clausius that no process is possible whose sole result is transfer of heat from colder object to hotter object, okay. So it seems like common sense, right? There cannot be any process by means of which what you can do is you can just transfer the heat from cold body to hot body. Okay, it is not possible. This is Clausius statement. Then there is Kelvin Planck's statement. No process is possible whose sole result is absorption of heat from a cold reservoir and complete conversion of heat into work. Okay, sorry, absorption of heat from a reservoir and complete conversion of that heat into work. Okay, so Kelvin Planck statement is that you cannot just absorb the heat and completely convert it to the work. What will happen? Some amount of heat, some amount of energy will be lost, because if you just absorb heat, let's suppose Q is the amount of heat absorbed, W is amount of work done. Okay, W is the amount of work done, then Q will be equal to W. That means your engine, whatever machine you are using to do this work, it will be 100% efficient, right? So in another way, we can say that there is no heat engine operating between two temperatures can have 100% efficiency. So there is no such engine which exists which operates between two temperatures which will have 100% efficiency. Okay, so these are the statements, right? So this one and this one is equivalent. No heat engine will have 100% efficiency. So we'll see why some engine or some machine cannot have 100% efficiency. Okay, what does efficiency means? Amount of work done divided by energy consumed. Okay, so this thing is clear. These statements are clear. All right. Now, what is a heat engine? What is a heat engine? So, heat engine is a machine which will absorb some heat from a hot reservoir. It will do some work and it will give out some heat to the cold reservoir. So there are two reservoirs. That means two bodies, two very big bodies, very big objects at two temperatures. So this one is at temperature T1, this one is at temperature T2, right? This is heat engine. This is simplistic diagram of heat engine. So you have a hot reservoir which is at temperature T1, cold reservoir which is at temperature T2, and your machine is in contact with these two reservoirs. So it will take amount Q1 of heat from this hot reservoir. It will do some work, and then what it will do is it will leave the remaining energy to the cold reservoir. Okay, so for an example, we can think of, you have suppose water. So suppose water here, and you give some heat to this water. Okay, you boil this water. What will happen? So this is your hot reservoir. Okay, so it will get converted to steam, right? It will get converted to steam. So you have given some energy, let's suppose Q1. Okay, from here. Okay, so you can have a flame or something. You can have a coal. Okay, which is at very high temperature. So let's suppose you have coal at very high temperature. So it will take heat from that coal. Okay, water will boil, and then you take that water, sorry, you take that steam, okay, from here to rotate a turbine, suppose. Okay, to rotate a turbine. So here you have a turbine. Okay, so I will draw a simple fan, right? So now what happens? The kinetic energy of this steam, part of it gets converted to what? The kinetic energy of this turbine. Okay, now the turbine will rotate, then we can connect some generator to it, and then the energy can be converted to what? The electricity. But now see what's happening. This steam, it is giving some part of its energy to this turbine, and then there is surrounding also, so it will lose some amount of energy in the form of heat that we call Q2. Okay, and then what you can do is you can again collect that. Okay, you can collect that steam and give it back to this container. Okay, so that the cycle will, it will keep on happening, right? So what are you doing? You are taking some heat Q1 from this coal, which is very hot coal, and you are doing some work, that is you are rotating the turbine. You are giving kinetic energy of the steam to the turbine. So some work W is done here, and then the remaining heat Q2 is given to what? It is given to the surrounding. So this is a simple kind of heat engine. Okay. So is this thing clear? Yes, no? So this is what it means by the heat engine operating between two temperatures. Okay. There will be a hot reservoir, there is a cold reservoir, and now this heat engine, it is in contact with what? These two reservoirs. So this one is at temperature T1. T1 is of course higher temperature. This is lower temperature T2. Okay, temperature of cold reservoir, and your engine does some work W. Okay. So now, how much would be the efficiency of this heat engine? So efficiency of this heat engine is equal to the amount of work done by this engine divided by the energy taken. Okay, energy taken is suppose Q1. How much is energy taken? It is Q1. So work done will be equal to Q1 minus Q2, right? It will be equal to Q1 minus Q2. So according to the law of conservation of energy, it is Q1 minus Q2. So you have Q1 minus Q2 divided by Q1. So it is 1 minus Q2 by Q1. Okay, Q1 upon Q1 is 1, right? And then now it can be found out that this efficiency is equal to what? 1 minus T2 by T1. Okay, so we have to remember this formula for the efficiency of this heat engine. Okay, so is this thing clear? All right. Next one is refrigerator. Okay, our home refrigerator. So it is nothing but it's a heat engine, but it is operated in opposite way. Okay, so this cycle is reversed. So what do you do here? So you have uh, again you have heat engine which is in contact with this hot reservoir and a cold reservoir. So temperature of this one is what? T1. Temperature of this one is T2. So what it will do is it will take some heat from the cold reservoir. Can you do that? By using the compressor you can do it. Okay, so see, what matters is the temperature of this refrigerator. Okay, temperature of the working substance. Okay, here we have used working substance as water. Okay, so there will be some kind of working substance, right? So temperature of that working substance will be very, very low. It is lower than the temperature of this cold reservoir. Then it will absorb some heat from the cold reservoir. Okay, then it is taking the heat from the cold reservoir. Why? Because its temperature is lower than cold reservoir. Okay, and then so that is how you are cooling. Okay, that is how the cooling will happen. And then what you will do is you will do some work on this working substance. Okay, so some electrical energy you can say it's given to this working substance or this heat engine. So now energy that it has is equal to what? It is equal to this Q2 which is taken from cold reservoir and the work W which is done on it. Okay, and then it will give up energy equal to Q1 to the hot reservoir. So now why are you doing some work on this heat engine or on the working substance? So by doing the work you are increasing its temperature. You are increasing its temperature and you are making it greater than what? Greater than hot reservoir. Okay, so that now when hot reservoir and this heat engine will come in contact with each other, the heat engine will lose energy to the hot reservoir. Okay, and that energy is equal to what? Q1, right? So this is clear. All right, so here now what do you want to do actually? You want to remove some heat from the cold reservoir. Okay, you want to cool this cold reservoir even more, right? So more you remove the heat, more efficient your machine will be. Okay, so here we don't find out the efficiency actually. So we find out a similar thing which is known as the performance parameter. Okay, or the coefficient of performance. It is denoted by beta. Okay, for a refrigerator, the coefficient of performance, it is denoted by beta. So what do you want to do? You want to remove some heat. Okay, so now in order to remove that heat and give it to the hot reservoir, what do you have to do? It is you have to do some work on this system. That means you have to give some energy, some outside energy, right? Maybe electricity. Okay, So in order to do this work, you need to provide some outside energy. Okay, so that is your cost. So performance parameter is what? It is beta. Beta is equal to Q2, the heat taken by it, divided by the energy that you have to supply. That is the amount of work that you are going to do. That is W. Okay, so Q2 divided by W. And again, using the law of conservation of energy, you can say that W is equal to this Q1 minus Q2. Okay, Q2 plus W will be equal to Q1. So W is equal to Q1 minus Q2. Okay, so then how much would be the performance parameter beta or coefficient of performance? It is Q2 divided by W, which is equal to Q1 minus Q2, or you can say it is equal to T2 divided by T1 minus T2. So this is the coefficient of performance of a refrigerator, right? This is clear. All right. Now after that, there was a French physicist whose name was Carnot or Carnot, right? And he came up with a engine, okay, idea of an engine which will be most efficient. So that engine will have most efficiency of all the engines, and if it is used as a refrigerator, then its performance parameter would be greatest. Okay, so it is a reversible engine. What is Carnot engine? It is a reversible engine. Okay, it operates between two temperatures T1 and T2, right? It's a reversible engine which operates between two temperatures T1 and T2. So Carnot found out that whatever operations you do on an engine, heat engine, they should be reversible in order to get the maximum efficiency. And he came up with a cycle, okay, which is known as Carnot cycle. Carnot cycle. Okay. So what is that Carnot cycle? So see, you have this heat engine which is operating between these two reservoirs. This is hot reservoir at temperature T1, okay, and you have cold reservoir at temperature T2, right? So now here, suppose your engine is very simple engine. This is gas in a container and you have a piston, okay, you have a piston. What you do is, now initially suppose you start from this point 1, so its pressure is P1, volume is V1. After that, what you do is you let it expand isothermally. Okay, so you let it expand isothermally. That means you give some amount of heat to this gas, and now boundaries of the system or this container, they are diathermic, right? And that's how the temperature between the system and surrounding will remain what? Constant. Okay, the system temperature will be equal to temperature of the surrounding. So then you let it expand isothermally. So what will happen? Some work will, it will take some heat, it will do some work. Okay, so suppose it takes QH or Q1 amount of heat. Okay, then so this isothermal expansion is complete. So at the end of this isothermal expansion, suppose its pressure becomes P2 and volume becomes V2. Of course, pressure will be lower, right? Volume will be higher. After that, what you do it is you let it expand adiabatically. So now what you do, you insert adiabatic walls. Okay, how you do it? It's your problem. It is designing problem. What you have to do? You have to insert insulating walls. Okay, so maybe there is some mechanism. There is, okay, you just drop those walls like this. Okay, so suppose wall at the bottom is adiabatic. Uh, okay, so some wall is adiabatic only, and other walls they can be moved, right? As you will. Okay, so now you make these walls adiabatic. Okay, and the system has got some entropy, you can say. Entropy means the molecules of the system, they are moving in random directions. So now they will keep on expanding. Okay, so system will keep on expanding. So you let it expand. Now you don't allow the heat to flow through the surrounding. Okay, so it goes from 2 to 3. Then it goes from suppose 2 to 3. So this is adiabatic expansion. There is no flow of heat from system to the surrounding. Okay, so then after that, what you do, you let this adiabatic expansion happen. Okay, then it will stop at some point. Then after that you compress it isothermally. Okay, you compress it isothermally, right? So now when you compress it isothermally, what will happen? It will give up some heat, right? For this process, for expansion, you will need some heat. For compression, what will happen? It will give up some heat. Okay, yes, no? Everything clear? Okay. So you can see the isotherm itself. This isotherm, uh, okay. If you see this isotherm and this isotherm, if you multiply P to V, okay, here on this isotherm and on this isotherm, the value of P times V will be greater here. That means this is at higher temperature and here it is at lower temperature. Okay. So what does it mean? So it will take some heat here and it will give up some heat here. Okay. So heat that it takes, it is suppose Q1, and heat that is it gives up, it is suppose Q2. Okay. In isothermal compression. So again, you go to some volume. Okay. V4 suppose from VT, V3 to V4, and then you stop that isothermal compression. And again, now you do adiabatic compression. Okay, you do adiabatic compression. That means again you insert the adiabatic walls, and then it goes from 4 to 1. Okay, it goes from 4 to 1. That means it goes back to its initial condition, its initial configuration, P1, V1, T1, right? So this happens adiabatically. So this is the Carnot cycle. Okay, and all these processes, this isothermal expansion is reversible isothermal expansion. That means it is very, very slow. At any point, you can reverse it. Okay, you are expanding it. At any point, you can begin compression. Is this thing clear? All these processes are reversible. Yes, no? All right. So this is the Carnot cycle. Okay, there can be a question based upon this Carnot cycle. Direct question, I mean conceptual question. Okay. Carnot cycle is completely reversible cycle. Okay, the points to be noted. Carnot cycle is completely reversible cycle. It consists of 4 processes. What are those 4 processes? So reversible isothermal expansion. Okay, then reversible adiabatic expansion, reversible isothermal compression, reversible adiabatic compression. Okay, these are the 4 processes, right? Okay, and then now this heat engine will have some efficiency because it has taken some heat here, okay, and here. Sorry, it has taken some heat here and it has given away some heat here, and it is doing some work in each of these cycles. Sorry, in each of these processes. This reversible um, isothermal compression, sorry, expansion, reversible isothermal compression, then reversible adiabatic expansion, reversible adiabatic compression. In all those processes, some work is happening, right? You add up all that work, so that will be your total work in this cycle, which will be equal to what? Area under this curve. We know this, okay? Work done in a cyclic process is area under PV curve, which is enclosed by that process, okay? So area under this curve will give us the work done. So that work done divided by the amount of heat taken. Q1 will be its efficiency. Okay, so efficiency has got the same formula as we saw for the heat engine. So it is equal to what? 1 minus T2 divided by T1, or 1 minus Q2 upon Q1. Okay, that is the efficiency of a Carnot engine. So is this thing clear? Yes, no? Any question is there on Carnot engine? Carnot engine. Okay. Now he came up with the idea of that engine, and then there is Carnot's theorem, which says that no heat engine operating between two given temperatures can be more efficient than a Carnot engine. Okay, so no heat engine which is operating between the same two temperatures can be more efficient than Carnot's engine. Okay, which is operating between the same two temperatures, right? So see the confidence, right? So is it the confidence or is there some law? So there is actually, yeah, there is second law of thermodynamics. Okay, second law of thermodynamics, which we saw, which says, yeah, heat cannot be completely converted to work. Okay, heat cannot be completely converted to work. So work done, what is efficiency? Efficiency is equal to what? Work done divided by heat consumed. So that is equal to Q1 minus Q2 upon Q1. Okay, this can be 100% if and only if what will happen? If no heat is given, right? It takes some heat, it does some work, and how much is the work? It is equal to amount of heat taken minus amount of heat given out or given away. Okay, so if heat engine doesn't give away any heat, so no heat is released, then the efficiency will be what? 100%. I will explain this to you. So efficiency will be 100% if and only if you have the second. Okay, efficiency will be 100% if everything else is perfect. No heat is given out. Okay, there is no friction. Okay, then there is no viscosity. That means there is no dissipative mechanism. And on top of that, now how much should be this T2? I want efficiency to be 100%. Okay, eta should be equal to what? 100%. That means T2 should be equal to 0, right? Yes, no. And what 0 is this? Is this 0 degrees Celsius? This is 0 Kelvin. Okay, so now nobody till date could achieve the temperature of any system equal to 0 Kelvin. Okay, temperature of 0 Kelvin. Now see, we have gone till some millikelvins, but still there is some disorder. What is temperature? Temperature is measure of disorder in the system. Okay, so if molecules or atoms or whatever electrons, suppose they are vibrating, they are moving in some random directions, okay, they will have some temperature. So now you have achieved temperature up to some millikelvins, but not absolute zero. If it is absolute zero, that means all the atomic and molecular activities, they will cease to happen. Okay, nothing will happen, they will not move at all. Okay, so this thing is impossible. Okay, in principle this thing is impossible, and that's why the efficiency equals to 100% is also impossible. Is this thing clear? Okay, so Carnot's theorem, it is based upon what? The second law of thermodynamics only. Okay, it's nothing else, right? And which engine will have the maximum amount of efficiency? It is the reversible engine only, which works by means of a Carnot cycle, which is a reversible cycle. Okay, so is this thing clear or is there any doubt? So now this is very, very important, because you will see that we'll now solve the problems, and there have been a lot of problems asked based upon the refrigerator, the heat engine, okay, and the Carnot's engine and Carnot cycle. Okay. So let's see this problem. The temperature inside a refrigerator is T2 degrees Celsius. Okay. So once you see degree Celsius, what should happen? Yeah. Convert it to Kelvin. Okay. And room temperature is T1 degrees Celsius. The amount of heat delivered to the room for each joule of electrical energy consumed ideally will be. So tell me, what do you know about the refrigerator? Which formula do you know? So what is performance parameter? Beta is equal to what? Q2 divided by W, which is Q2 upon Q1 minus Q2. Or you can say it is equal to what? T2 upon T1 minus T2. But this T2 and T1 minus T2, they will be in kelvins. Okay. So it is T2 plus 273 divided by, in denominator you will have T1 plus 273 and minus, this will be T2 plus 273. Okay. 273 and 273 will get cancelled. Your answer would be T2 plus 273 divided by T1 minus T2. Okay. So this is clear, right? All right. So then let's come to the next question. A refrigerator works between 4 degrees Celsius and 30 degrees Celsius. It is required to remove 600 calories of heat every second in order to keep the temperature of the refrigerated space constant. Okay. So what is this 600 calories? Is it Q1 or Q2? This is Q2. Okay. In refrigerator, we remove heat from the cold reservoir. Okay. So this is Q2. It is equal to 600 calories. And now what do you have to do? The power required is, take 1 calorie equals to 4.2 joules. So what is power? Power is equal to work done per unit time. Okay, that means you have to find out what is work done, right? So tell me, what will you do? Again, these questions are very simple. You just have to remember, if it is heat engine, the efficiency; if it is the refrigerator, then performance coefficient. So beta, it is equal to what? Q2 upon W, which is Q1 minus Q2. So you want to find out W, you already have Q2 and you have two temperatures. Okay, so this is 4 degrees Celsius, this is 30 degree Celsius. Tell me. So it will be T1, sorry, T2 upon T1 minus T2. So what is T2? 4 degrees Celsius. How much is it in Kelvin? Yeah, but it is 4 degrees Celsius, no? 277. And how much is T1? It is 30 degrees Celsius. So it is 303, 303. And T2 is again 277. Okay, so difference we can take directly, right? It is 30 minus 4. That will be easier, because in both of them we are just adding 273, right? Okay, so this is Q2 upon W. Q2 is given, it is 600 calories. So this is 26. Okay, instead of this, I will just write 26. Now how much would be W? W is equal to 600 multiplied by 26 divided by 277. Right, this is correct. Okay. So then uh, seems like little bit of difficult calculation. So then this will be in calories. We have to convert it to joules also. Okay, so you have 600 times 26 multiplied by 4.2 divided by 277 in joules. So you can't do round figure also. Okay. We can multiply this with this. Okay, we just want order of magnitude because the order of magnitude of all these options is different. This is 2 point something, this is what? 23.65. So this is okay, 2365. We just want order of magnitude, right? So there comes simplification. So I will just say this is equal to 10. Okay, it will be little bit greater than that, but we don't care now. And this is 600 times 4. So it is 2400 divided by 10. So nearly roughly equal to 240. Okay, so it is option A, right? This is simple. Okay, so calculation was difficult, but options are very far. So we can do round figure. Okay, all right. Let's see next one. The coefficient of performance of a refrigerator is 5. If the temperature inside freezer is minus 20 degrees Celsius, the temperature of the surrounding to which it rejects heat is. Tell me. Okay, it is T2 upon T1 minus T2. So beta is given. Beta is 5. How much is T2? Temperature inside freezer is T2 minus 20 degrees Celsius. How much in kelvins? 253, not 93. This is minus 20, no? Plus 20. So this will be 253. And in denominator, you will have, you want to find out T1. This is 253, right? So then you can move it on this side. So you get 5 times T1 minus 5 times 253 is equal to 253. Okay. Actually, you could just keep T2 and T2 here, multiply it, do cross multiplication, I will say. Okay. So let's just say that this is T2, this is T1 minus T2. Okay. And at the last, at the end, you can substitute the numerical values. It will save you some time, right? So this will be 5 times T1 minus 5 times T2 and it's equal to T2. Okay. So how much is this? Take this on other side. So it will be 6 times T2 is equal to T1. 5 times T1. So 5 T1 equals to 6 times T2, which means that T1 is equal to what? 6 by 5 T2. So that is how much? 6 by 5 multiplied by was 253. Okay, minus 20 degrees Celsius, right? So this is how much? 25 divided by 5 is 5. Then it's 50.6, right? So 50 times 6 is how much? 300, and 6 times 6. So this is 300. Okay, 6 times 6 is 36. 303.6 in kelvins. Okay, so minus 273, right, in degrees Celsius. So minus 273. So it is equal to how much? 30, 31, 30.6. So this is the answer. Option C. So this is clear, right? All the questions will be like this only. There is nothing difficult. Okay, tell me this one. Which of the following processes is reversible? Transfer of heat by conduction, transfer of heat by radiation, isothermal compression, and D, electrical heating of nichrome wire. Think of which one of these can be reversed. Is it option C? Yes, others cannot be reversed because in this one you have some medium where you have temperature T1, okay, of one reservoir, another is at temperature T2, okay, and heat flows from higher to lower temperature. It cannot be reversed. It cannot be made to flow from lower to higher temperature, okay, unless some work is done, right? Unless some work is done means unless some energy is taken from the universe, and we have seen that in reversible process we don't do any change on the universe, right? So this is not reversible. Heat will always flow from higher to lower temperature. Then transfer of heat by radiations. So radiation is electromagnetic waves, okay? Radiation is electromagnetic waves. Once that heat is lost in form of radiation, it goes by the speed of what? What is speed of electromagnetic waves? 3 into 10 raised to 8 meters per second. Why would they come back? They cannot come back, right? Unless some external force is applied from other side. Okay, unless those photons, we can say we'll learn about photons afterwards. So unless these electromagnetic waves they strike with some mirror, they can't come back. Okay, so this transfer of heat by radiation, this thing also it is not reversible at all. Then this one, electrical heating of nichrome wire. So once you give electrical energy, once you pass the current, what happens? Electrical energy is lost. It gets converted to heat. Now, can you convert that heat on the nichrome wire to the same electrical energy? You can't do that. Okay, it won't happen that heat automatically will get converted to electrical energy and it will flow back to the plug. Okay, from plug to the generator. It won't happen. This is not reversible. Okay, so only thing which can be reversible is isothermal compression. Okay, all right. So this is simple question, and in fact, in examples also we have seen reversible isothermal compression. Okay, quasi-static isothermal compression and quasi-static isothermal expansion. Quasi-static any process is what? Reversible process. Okay, a Carnot engine having efficiency 1 by 10 as a heat engine is used as a refrigerator. So you have efficiency eta equals to what? 1 by 10. If work done on the system is 10 joule, work done on the system is what? 10 joule. The amount of heat absorbed from the reservoir at low temperature is. This is the question. Okay, so this is a heat engine, right? So what is eta in terms of work done? But eta is equal to what? W divided by Q1, right? So eta is W upon Q1. It's 1 by 10, right? So then what we can do is W is given, we can find out Q1, right? W is given. How much is W? W is 10 joules. Okay, so W is 10 joules. Put that. So W upon Q1 is equal to 1 by 10. Okay, which means that Q1 is equal to what? 100 joules. Okay, and then the amount of energy absorbed from the reservoir at low temperature is, tell me, Q2 will be equal to what? It's the amount of energy absorbed from the reservoir at low temperature. So it is equal to Q1 minus W, that is equal to 100 minus 10, right? 90 joules. Okay, so actually a simple problem. No need to take that long route. Okay, so what we did earlier was longer route. What we did, we took eta, and from eta we found beta, and then from beta we found, okay, Q2. Okay, so it can be solved in this way. This is simple. Yes, no? All right, good. So then this thing we can remember, that if there is a heat engine, okay, it is so there can be question like this. There is a heat engine, okay, its efficiency might be given. Then if it is operated as a refrigerator, then performance parameter is given, suppose. So eta and beta are given. Okay, then if it takes amount of okay, heat equal to Q2, how much will be heat given to the, hot reservoir when it is used as a refrigerator? Okay, so eta times beta will also be equal to what? Q2 by Q1, right? So we can remember this thing, and then if there is question like that, it can be solved this way. Okay, so then let's move on to the next problem. Two Carnot engines A and B are operated in series. So they are operated in series. Okay, the engine A receives heat from the source at temperature T1 and rejects the heat to the sink at temperature T. So first one takes heat from the hot reservoir, okay, at T1, and it gives to cold reservoir at temperature T. This is your heat engine. Okay. The second engine B receives the heat at temperature T. Okay. So it receives heat from here, from this cold reservoir. It receives heat T and rejects it to I'm sorry, rejects it to the sink. There is colder one. Okay. At temperature T2. For what value of T? For what value of this T? The efficiencies of two engines are equal. Oh, so this is simple. So eta 1 equals to eta 2. Okay, for eta 1 it is what? 1 minus, yeah, it is releasing at the reservoir which is at temperature T, right? For first engine, T2 is equal to T, right? Yes, no? Okay, so it is T upon T1, 1 minus T upon T1. This is efficiency of first engine. Efficiency of second engine, for this one, it is taking heat from this one. So this is hot reservoir for it. Okay, and this is cold reservoir for it. So it is equal to 1 minus the colder one is at temperature T2, and the reservoir which is hot for it, it is at temperature T, right? Yes, no? Okay. So then this 1 will get cancelled. Okay, and this negative sign also gets cancelled. You have T upon T1 equals to T2 upon T. That implies T square is equal to T1 T2 and T is equal to root of T1 T2. Okay, so this is very simple problem. This is clear. There is nothing in it. All right. Let's see next one. Carnot engine whose sink is at 300 Kelvin has an efficiency of 40%. By how much should the temperature of source be increased so as to increase its efficiency by 50% of the original efficiency? Okay, you want to increase the efficiency by 50% of original efficiency. So what is given? That E dash is equal to what? 50% extra. So 150% of, right, of eta. So eta is original efficiency, which is 40%, and you are increasing this by 50%. Yes, no? So it is 150% of eta. How much is this? 150% of 40% will be 60%, right? 200% will be 80%. Okay, see, 150% is 150 divided by 100 of 40%. Okay, so this is 40 upon 100. Okay, so this is equal to 3 by 2. So this will be how much? 20, right? So 40 by 2 is 20. 20 times 3 is 60. 60 by 100. Okay, you can just say it is 150% of 40%. How much would be double of 40%? That is 200% of 40%. It's 80%. So how much would be 150%? It's 60%. Okay, no need to do all this. All right. So this is clear, right? So eta dash is equal to 60%. Okay. Then what's given? Sink is at 300 Kelvin. So cold reservoir. Sink means cold reservoir. Source means hot reservoir. So cold reservoir is at 300 Kelvins. Okay. So efficiency can be written as 1 minus T2 upon T1. Okay. So T2 is given, that's 300. So now you have 1 minus T2 by T1. So T2 is how much? It is 300. You can find out T1. So it is 1 minus how much? 300 divided by T1 is equal to 40%. This is 40 by 100. Okay. So therefore, move this on this side. So 300 upon T1 will be equal to what? 1 minus 40 by 100, that is 60 by 100. Can I say this? Because 1 is how much? 100 by 100. Okay, 60 by 100. Then what do you get? How much would be T1? So T1 will be equal to with just 300 times 100 divided by 60. Okay, so this will be 5. 5 times 100 is 500. Right? Okay. So you found T1, and now question is how much should it be increased so that efficiency increases by what? Efficiency increases by 50%. That means efficiency becomes now, it was 40%, increases by 50%. Okay, so that is 50% of 40. Okay, that is 20%, increases by 20%. It becomes 60%. Okay, so what will be new T1? Tell me. So eta dash is equal to 1 minus T2 upon T1 dash, right? So eta dash will be equal to what? It is 60 by 100. It is 1 minus T2 is 300. T1 is how much? T1 dash we have to find out, right? So you have 300 upon T1 dash equals to 1 minus 60 by 100. So that is 40 by 100. That will give you T1 dash equal to 300 times 100 upon 40. How much is this? So this is 3 by 4, right? So this will be 7.5 times 100, 750. Okay. So you have initial T1, you have final T1, final value of T1, T1 dash. So how much is change? Change is T1 dash minus T1. That is 750 minus 500. So 250 Kelvin is the answer. Okay. Option D. So this is clear. Okay. So it might seem lengthy. It is not lengthy actually. Okay. This part you have to do it in mind. Okay. So you don't have to do all these steps. What is final efficiency? It increases by 50%. What is initial one? It is 40. Okay. So how much is 50% of 40? 20. So it increases by 20. That means final efficiency becomes 60. Okay. So you need to do only this thing and this thing. That's it. So question is simple. Yes, no. All right. Your response has slowed down. It's simple, no? All right. These questions might be little bit lengthy, but they are sure shot. Okay, you can 100% solve these questions, right? An ideal gas heat engine operates in Carnot cycle between 227 degrees Celsius and 127 degrees Celsius. It absorbs 6 multiplied by 10 raised to 4 calorie of heat at higher temperature. Okay, the amount of heat converted to work is, tell me. So there are two temperatures, okay, and it's a Carnot engine and it absorbs this much heat, okay. So how much is efficiency? Right. This W by Q1, it is equal to T1 minus T2 divided by T1. And how much is this T1, T2? How much is difference? 100. And T1 is how much? It is 227, right? This is T1, this is T2. 227 in degrees Celsius. So how much in Kelvin? 500. Okay. And W you don't know. Q1 you know. It is absorbing this much heat. So it is 6 into 10 raised to 4. So this thing is 1 by 5. Okay. So 5 times W is equal to 6 into 10 raised to 4. That means W is equal to what? 6 into 10 raised to 4 divided by 5. So it's 1.2 multiplied by 10 raised to 4 calories. Options are in calories? Yes. So answer is option D. This one is very simple. right? Only one step. Okay, in earlier questions, some questions there were two steps. Okay, so next question, an ideal gas heat engine operates in Carnot cycle between 227 degrees Celsius and 127 degrees Celsius. It absorbs 6 kilocalorie at higher temperature. Okay, so this is 2005, this is 2003. One change is there. So this is 6 into 10 raised to 4. This is 6 kilocalories. Okay, at the higher temperature, the amount of heat in kilocalorie converted into work is equal to, tell me, it's option D. Okay, we have to solve it exactly same way, the earlier one. Okay, right. Let's see next one. The efficiency of Carnot cycle is 50% and temperature of sink is 500 Kelvin. If temperature of source is kept constant and its efficiency raised to 60%. Okay, so here there are two steps. You can see that. Okay, one efficiency is given, then efficiency is changed. Okay, so two steps. It's going to be little bit lengthy, but process is there. You can solve it. Okay, then the required temperature of the sink will be. Okay, tell me. T2 is known. We'll get relation between. Yes. Okay. So eta is equal to what? It is 1 minus T2 by T1. Okay, and what is given? The temperature of sink is 500 kelvins. So T2 is given. And this is 50% means it is equal to 1 by 2. Right? 50% means 50 by 100. That's 1 by 2. 1 by 2 is 1 minus T2 by T1. So what does it mean? So 1 minus something is equal to half. That means this is equal to half. T2 by T1 is equal to half. So temperature of sink is given, which is 500 kelvins. So T2 is 500. That means T1 is equal to what? 2 times of T2, that is 1000 Kelvin. So you got T1. Then now what are you doing? You are keeping the temperature of source constant. So T1 is kept constant, the same. Okay, source is kept constant and efficiency is raised to 60. So required temperature of sink. So now how much will be T2 dash? This is the question. So eta dash is equal to 1 minus T2 dash upon T1. Okay. So this is now 60%. So it is 60 by 100 is equal to 1 minus T2 dash divided by 1000. Okay. This is 60 by 100. That means 1 minus T2 dash upon 1000 is 60 by 100. Okay. So how much is this? This one will be equal to then 40 by 100. Okay. Or move this on this side. Move this thing on this side. So T2 dash upon 1000 is equal to 1 minus 60 by 100. T2 dash divided by 1000 is equal to 1 minus 60 by 100 means it is 40 by 100. Okay. So then you can just increase one zero in the numerator and denominator and cancel out denominator. So T2 dash will be equal to what? 400 kelvins. Okay. So it's option C. Right. Okay. So there are two steps, but it is not difficult. Right. Little lengthy, but this is sure shot. And there have been lot of questions. You can see there have been lot of questions on these things. This chapter is very important. Okay. Thermodynamics is important chapter. All right. So a scientist says that efficiency of his heat engine, which work at source temperature 127 degrees Celsius and sink temperature 27 degrees Celsius, is 26%. Then option A, it is impossible. Option B, it is possible but less probable. Option C, it is quite probable. Option D, data are incomplete. Okay. So what is the scientist saying? He's saying that efficiency of its heat engine which work at source temperature 127 degrees Celsius, and sink 27 degrees Celsius is 26%. So let us check his claim. Okay, so how much is efficiency? We know it cannot be greater than efficiency of Carnot engine, that is 1 minus T2 by T1. Okay, and T1 T2 we have to convert in kelvins. Okay, so this is 27 degrees Celsius meaning 300 kelvins, and this is 127 meaning 400 kelvins. So 1 minus 300 by 400. So this is 3 by 4, 0.75. 1 minus 0.75 is 0.25. Okay, in percentage, it is equal to 25%. Okay, so Carnot says that it can be at max equals to 25% for these two temperatures, and this scientist is claiming, okay, that it is 26%. His engine is providing 26%. So is it possible? Yes, no? What is Carnot theorem? What does it say? That no heat engine can be made whose efficiency is greater than Carnot's engine if it is operating between the same two temperatures, right? So this is not possible, right? It is impossible. Yes, no? Okay. So different people, they claimed that they have designed a machine whose efficiency is greater than Carnot's engine. Okay. And literally thousands of patents were filed. Okay, you can just search this on internet. Thousands of patents were filed, but all of them failed. Okay, and a scientist, at least a scientist, will not do such kind of a mistake. Okay, all right. So I have a problem with this question. Scientist will not do this. Anyways, he will first check Carnot's theorem. Okay, and if scientist wants to do it, then he will try to find out ways to falsify the Carnot's theorem. Okay, which is actually based upon the fundamental law, second law of thermodynamics. So it is not falsifiable. All right. So these kind of claims are impossible. Anyways, let us see next question. The W by Q of Carnot engine is 1 by 6. Now the temperature of sink is reduced by 62%. Then this ratio becomes twice. Therefore, the initial temperature of the sink and the source are respectively. Okay, so again there are two steps, but we can solve this. Okay, so W by Q. Okay, so eta is what? It is 1 minus T2 by T1. Okay, and this is 1 by 6. This is given to be 1 by 6 is 1 minus T2 by T1. So from this, what you can do is you can find out T2 by T1. So move T2 by T1 on this side. Yes, it will be equal to 5 by 6. T2 by T1 is equal to 5 by 6, and therefore you will get what? 6T2 is equal to 5T1. So let's keep it as it is for now. Then what you are doing? You are decreasing T2. And what's happening? When you decrease T2 by 62, the efficiency becomes twice. So eta dash is equal to 1 minus T2 dash by T1. So this is twice of first one. That means this is 2 by 6. Okay. This is 2 by 6. That means it is 1 by 3, and it's equal to 1 minus T2 dash by T1. So that means this will be T2 dash upon T1 will be equal to what? 2 by 3. Okay. So T2 dash is equal to what? It is equal to, yes, it is 2 by 3 times T1. It is equal to what? T2 minus 62. So it is equal to 2 by 3 T1, and from here you have one relation for T1. T1 is equal to 6 by 5 T2. We can substitute that here. It is equal to 6 by 5. So 2 by 3 times 6 by 5 times T2 is equal to T2 minus 62. Okay. Yeah. So it is 4 by 5 T2. So we have 4 by 5 T2. T2 minus 62 is equal to 4 by 5 times T2, right? I'm doing no mistake. Okay. So 5 times T2 minus 62 multiplied by 5 is 4 times T2. That means if we move this 4 times T2 on this side, it will be T2 only. So T2 is equal to 62 times 5. How much is this? This is 310 in kelvins. Okay, right. And then you have T1. So T1 we can find out either from this one or from this one. So T2 upon T1 is 5 by 6. T2 by T1 is 5 by 6. So that is equal to 310 divided by T1 is 5 by 6. So let's move this. So T1 will be equal to what? 310 times 6 upon 5. Okay, so that is 62 times 6. How much? 372 kelvins. So one is 310 Kelvin, other one is 372 kelvins. So the options are, it is in degree Celsius. This one is in Kelvin, but this is not correct. So 310 kelvins. Subtract 273. How much will this be? So it will be 27 plus this extra 10. Okay, 37. Right? And this is 37. Let's check 37. Yes, this will be the answer. This is 372. It is 99. Okay, in degrees Celsius. So answer is option B, 37 degrees Celsius and 99 degree Celsius. Right? Next one, the efficiency of Carnot engine operating with reservoir temperature of 100 degrees Celsius and minus 23 degrees Celsius. So this minus sign is important. Minus 23 degrees Celsius will be. Tell me, so Carnot's engine, T1 minus T2 upon T1, right? So it is 100 degrees Celsius is how much? 373, right? 100 plus 273 minus it is 273 plus this temperature minus 23. How much? 250. 250 only. Okay. Divided by 373. So which one is correct? Option B. Okay. See, if somebody uses this formula and doesn't convert, then there would be option for that one also. Yes. So minus minus will become plus, right? 100 plus minus 23. Okay, 100 minus minus 23. That minus minus becomes plus. So 100 plus 23 upon 100. Okay. This is just to create a confusion. Anyway, so this is very simple, right? Let's see next one. An ideal Carnot engine whose efficiency is 40% receives heat at 500 Kelvin. Its efficiency is, if its efficiency is 50%, then the intake temperature for the same exhaust temperature is. Okay, so tell me. Again, efficiency is, yeah, 40 by 100. It is equal to 1 minus T2 by T1. So this is 40%. That means T2 by T1 will be what? 60%. Okay. So T2 by T1 on this side, it will be 1 minus 40 by 100. That is 60 by 100. T2 upon T1 is 60 by 100. Sorry. Or you can say it is equal to 6 by 10 or 3 by 5. And it receives heat at 500 Kelvin. What does it mean? Is it T1 or T2? It is T1. Good. So T1 is 500. Okay. So T2 upon 500 is equal to 3 by 5. Yes. T2 will be equal to 300 Kelvin. And then what is done? Now efficiency is 50%. Okay. So eta dash is equal to 50%. So that is equal to what? 1 minus, yeah, so 1 by 2. Okay, 50 by 100 is 1 by 2. That's 1 minus what is changed? Then the intake temperature at same exhaust temperature. Exhaust means it is giving out. T2 is kept same. Okay, T1 is changed. Exhaust means you give out. Okay, so T2 is kept same exhaust temperature. Sink is same. Okay, exhaust is same. T1 is changed. So T2 is 300. This is half. That means T2 by T1 is T2 dash. Not T2 dash. T2 is kept same. T2 by T1 dash is half. Okay. So T2 upon T1 dash is half, and T2 is equal to how much? It is 300. So 300 by T1 dash is half. That means T1 dash is equal to 600, right? 600 kelvins. Okay, good. So I guess this was last problem. So this thing is clear, right? We have solved. Okay, these were 2-3 topics only, short topics, and we have solved lots of problems. Why? Because there were lots of problems asked on these things. Okay, so this thing should be clear. Most probably there is a problem. Okay, you can see that 1995, 97, whatever, 2000, 2001, 2, 3, 5, okay, 6, then okay, 2013, okay, 15, 17, 5, okay, 15. So they are not in order. Okay, so there are questions based upon these things, right? Okay, so do this carefully. And in the question where this thing is given, what is given? Work done and heat is given, and efficiency or performance coefficient is given. Then use the formula in terms of work done and heat. Where temperature is given, use that formula. Where both are given, you have to compare. You know what to do. Okay, use what? Q2 by W and this formula, right? T2 upon T1 minus T2. So the two temperatures will be given. Either of these two will be given, either work done or Q2 or Q1. Okay, and you have to find the left out thing. Okay, so this is simple, right? Good. So we'll stop here. So this is end of another chapter.